The universe is expanding, yet there is no outside, no edge, no cosmic wall to push against. Every second, space itself is stretching, and the map of reality is rewriting under your feet. So if everything is getting bigger, what could it possibly be expanding into? How do you grow when there's nowhere to go? Picture the most distant galaxies as lanterns on a moving sea. Each photon arrives with a story it cannot tell plainly. What looks like motion may be something far stranger, reality's ruler itself changing length. To face this paradox, we have to abandon the comfort of everyday space, rooms, roads, horizons, and learn a new kind of distance. In cosmology, where is not just location, it is geometry, written into the fabric that measures every separation. Across billions of years, light has been stretched into redder colours, not by fatigue, but by a shifting cosmic scale. That shift is subtle in a spectrum, yet immense in consequence, because it turns starlight into a measurement of the universe's history. But history is not a simple timeline pinned to a fixed stage. In Einstein's universe, the stage participates, and the script includes the rulers and clocks we use to read it. If space-time is dynamic, then our instincts about edges, centres, and empty rooms can mislead us before we even begin. We will follow the evidence where it actually lives, in the fine print of absorption lines, the calibrated glow of standard candles, and the afterimage of a sky once hot enough to shine like a furnace. We will watch those clues converge independently on the same unsettling conclusion. The cosmos changes its scale without needing a surrounding backdrop, and we will confront the word that causes the most confusion: nothing. Empty space is not featureless, the vacuum is not void, and the absence of geometry is a different category altogether. When these meanings blur, the mind invents an imaginary outside, and the paradox feels unavoidable. So this journey is not a hunt for a border beyond the stars. It is an investigation into what space even is, how expansion becomes a statement about the metric, and why the earliest moments resist ordinary language. Along the way, we will meet horizons that behave like limits without walls, accelerations that arrive late in cosmic time, and a universe whose future may be shaped by a pressure we barely understand. By the end, the central question will look different, not smaller, but sharper. The deepest puzzle may not be what surrounds the universe, but why there is a geometry to evolve, laws to follow, and time to carry change forward. Before we begin, let us know in the comments below where in the world you're watching from and what time it is there. Now, settle in for a journey. From intuitive analogies to hard observations, we'll build the case step by step, then test it against geometry, inflation, and dark energy. Each chapter narrows the language until the paradox has nowhere left to hide. Picture a balloon as it inflates, dots drifting apart across its skin. The latex brightens under studio lights, and the dots, tiny ink galaxies, seem to slide away from one another. Look closely, and something unsettling happens. No dot can honestly claim to be the centre of expansion, even though every dot sees the same pattern. The surface grows, yet the surface has no edge to cross, no rim where the rubber ends. That simple image triggers a stubborn question about our universe. If everything is expanding, what is it expanding into? Our instincts demand an outside because our bodies learned physics in rooms. In daily life, growth means taking up more room in a larger room, and we can point to the air that gets displaced. A fireball expands into surrounding gas, and a shockwave spreads through a medium that carries pressure. Even an inflating balloon expands into the space around it, pushing against the atmosphere and your hands. We carry that intuition into cosmology, and then we collide with a paradox. The universe appears to expand, but the universe is all the space there is. The contradiction feels obvious once you say it out loud. Expansion seems to require a boundary, and a boundary seems to require something beyond it. If there is a beyond, then the universe is not everything, and our definition collapses. If there is no beyond, then expansion sounds like a word without meaning, like growth without room. This documentary begins inside that discomfort, because the discomfort reveals a hidden assumption. We assume space is a stage that exists before anything happens, and we imagine matter as actors moving across it. The balloon metaphor is not about rubber, and it is not about air. It is about geometry, and about what it means to measure distance on a surface. On the balloon's skin, every point can say every other point is receding, and that statement is true in every direction. No point needs to be special for the pattern to hold, because the rule is built into the surface itself. The expansion is intrinsic, meaning it is defined within the surface, using only distances measured along it. The outside space that the balloon inflates into is not part of the surface story, even if our eyes keep drifting there. That is the first clue, and it is more than a metaphorical trick. When cosmologists say the universe expands, they do not mean galaxies fly through space away from a central blast. They mean the distances defined by space itself change with time, even when local motion is small. The expansion is a property of the metric, the rule that turns coordinates into measured lengths and times. In plain language, the ruler you would use to measure the cosmos is being rescaled by the cosmos. The universe is not a cloud of debris moving into emptiness. It is a changing set of relationships that we call space-time. Still, the word Big Bang keeps pulling us back to an explosion. The phrase suggests a bomb, a point, and a surrounding void, because that is how explosions behave in our world. It suggests a moment when matter erupted into pre-existing darkness, and then cooled as it spread out. That picture is powerful, and it is wrong in the specific way that matters here. The Big Bang model describes an early state that was hot, dense, and rapidly evolving everywhere. Not a spark at one address. It does not place the beginning at a single location in an older space, because older space is not part of the model. Historically, even this idea had to fight for oxygen. In the early 20th century, many scientists preferred a static universe, partly because it felt philosophically stable. Einstein himself introduced a cosmological constant to hold the universe still, because his equations otherwise implied change. Then observations began to force a different story, and the mathematics stopped being optional. The Big Bang framework emerged as a description of a universe whose scale changes and whose temperature and density evolve with that scale. It is not a cinematic blast wave, even if the name keeps tempting us. In the standard view, there was no empty arena waiting for the universe to fill. Space-time itself is part of what is described by the theory, and the stage is one of the actors. When we run the cosmic history backward, we do not find a center in space where everything started. We find conditions becoming more extreme throughout space, as the scale factor shrinks and densities rise. The question shifts from where the explosion happened to what the equations say about time, density, and geometry. That shift sounds abstract, but it is anchored to measurements. But the paradox survives the correction, because our imagination keeps rebuilding the old picture. Even if expansion is intrinsic, we still ask what it means to get bigger, as if bigger must mean embedded in larger. We still picture a volume that must be surrounded by something, because that is how containers work. We still imagine an edge, even if we cannot locate it, because edges are how we end a thought. Our language keeps sneaking the outside back in, and the universe refuses to cooperate. That is why the phrase, expanding into nothing, is so sticky. To untangle it, we have to notice that nothing is not one idea. In everyday speech, nothing often means empty space, like a dark room with the furniture removed. In physics, nothing can mean no matter and no radiation, but still with space and time present, like an idealized vacuum. In deeper cosmological questions, nothing can mean no space, no time, no geometry at all, not even a place for laws to sit. These meanings are not interchangeable, yet we swap them without noticing, and then we wonder why the sentence feels haunted. If nothing means empty space, then expansion sounds like filling a void, as if the universe were a gas leaking outward. If nothing means absence of matter, then expansion could occur in a universe that is mostly vacuum, with galaxies as rare islands. If nothing means absence of space-time, then the phrase into nothing becomes almost grammatical nonsense. There is no into without a place to go and no before without time to order events. The central confusion is partly a confusion of definitions, and partly a confusion of what our words were built to describe. Cosmology uses these definitions carefully, because the observations force it to be precise. The universe is not a philosophical guess, and it is not a myth dressed up in equations. It is measured, mapped, and tested against models that can fail in public. The key evidence for expansion is not a thought experiment, and it is not a metaphor stretched too far. It is a pattern in light that arrives at our telescopes, recorded as lines and numbers. Even the mystery begins with data. In the early 20th century, astronomers began to notice that many galaxies have redshifted spectra. Their light is stretched toward longer wavelengths, so familiar absorption lines slide toward the red end of the rainbow. This is not a subjective colour change, but a shift you can measure with a spectrograph. Edwin Hubble and others connected that redshift to distance, using standard candles and careful calibration. Cepheid variable stars, with their period, luminosity relation, became one of the crucial rungs on that distance ladder. The farther the galaxy, the larger the redshift, in a roughly linear relation. The simplest reading is that distant galaxies are receding faster. This is not a vague impression, and it is not a single dramatic photograph. Redshift is a measurable displacement of known spectral lines, like fingerprints moved along a ruler. Distance can be estimated by independent methods, with uncertainties that can be improved and cross-checked. When the relationship persists across many galaxies, it becomes a law-like feature of the cosmos, not a convenient story. The universe is not static, and the evidence is written into the colour of starlight line by line. At first glance, recession sounds like motion through space, like shrapnel flying outward. That interpretation is tempting, because it matches our everyday experience of velocity and distance. Yet in general relativity, recession can be the result of expanding space between objects, even when the objects are locally calm. The galaxies can be nearly at rest in their local neighbourhoods, bound by gravity in groups and clusters. Meanwhile, the large-scale metric changes, and the separation between distant regions grows. The redshift then becomes a record of stretched space, not only of Doppler motion. This is where the balloon returns, now as a conceptual tool rather than a picture. On the balloon's surface, dots can remain fixed on the rubber, while distances between them increase as the rubber stretches. No dot travels across the surface to make that happen, and no dot needs a rocket engine. The surface itself changes its scale, and the geometry does the work. In cosmology, co-moving galaxies play the role of those dots, carried along by the overall expansion. Their coordinates can stay the same while the metric distance grows. The analogy is limited, and we will keep its limits in view because limits are where misconceptions breed. The balloon has an outside and the universe may not, so the visual can smuggle in the very beyond we are trying to question. The balloon surface is two-dimensional, and our space is three-dimensional, so the embedding is easier to picture than it should be. The balloon expands in time that exists independently of the balloon, while cosmic time is part of space-time itself. The value of the analogy is not the rubber, and it is not the air. The value is the idea of intrinsic geometry, where distance can change without invoking an external container. So why does the paradox feel so unavoidable, even after the explanation? Because our brains are trained on embedded objects, and our senses are built for local scales. We learn space by moving through it and by watching objects move within it, and we learn boundaries by touching walls and seeing horizons. We learn expansion by watching things spread out into surrounding room, and we learn outside as a practical necessity. We rarely experience the metric itself changing, so we default to the stage metaphor. In a sense, our intuition is optimized for survival, not for cosmological bookkeeping. Relativity asks us to drop that metaphor, and it does so with a kind of quiet ruthlessness. Space and time are not passive containers, and they are not fixed background scenery. They are dynamical, shaped by energy and momentum, and described by equations that link matter to curvature. The geometry can curve, and the scale can evolve, and those changes affect how light travels and how clocks tick. In that framework, asking what the universe expands into can be like asking what the surface of Earth curves into, if you only live on the surface. The question assumes an embedding that the internal geometry does not require, even if the embedding is easy to imagine. Yet even that answer can feel like a dodge, because it denies the craving for a picture. If there is no edge, how can there be growth, and what does more space even mean? If there is no outside, how can there be a larger volume, and what would it be larger than? If the universe is all there is, how can it change size without a reference, and who gets to define the scale? These are not childish questions, and they are not mere word games. They are the exact points where intuition meets the limits of everyday language, and where physics has to be more careful than poetry. We can sharpen the tension by naming what we actually observe and what we do not. We observe that light from distant galaxies is redshifted, and that the amount of redshift tracks distance in a systematic way. We observed that the cosmic microwave background is a cooled remnant of a hotter past, now bathing the sky in microwaves with an almost perfect blackbody spectrum. We observe large-scale uniformity with small fluctuations, and those tiny variations grew into galaxies and clusters. These observations are consistent with an expanding universe described by a scale factor that changes with time. None of them directly show an edge, and none of them demand an outside. The edge is something we imagine because we confuse the observable universe with the whole universe. Our observable region is bounded by a horizon, set by the finite speed of light and the age of the cosmos. That horizon is not a wall in space, and it is not a physical border you could crash into. It is a limit on what signals have had time to reach us, given the universe's history of expansion. Confusing horizon with boundary makes the outside feel necessary, because boundaries invite the question of what lies beyond. Horizons are different, and the difference matters. Another source of confusion is the word beginning, which carries hidden grammar. When we say the universe had a beginning, we picture a time before it, like a blank page before the first sentence. But if time is part of the universe, before may not be defined in the usual way, because there is no external clock. The Big Bang is not necessarily a first moment in a larger timeline, and it is not automatically a creation event. It is a limit of our current descriptions, a place where known physics may break, and where our equations stop being trustworthy guides. So the phrase, expanding into nothing, mixes several questions, and each question tugs on a different meaning of the same words. What is space, if it can stretch? And what does stretching mean when no material is being pulled? What is nothing, if it can be a vacuum or an absence of geometry? And why do we keep sliding between those ideas? What is expansion, if it is not motion through an external medium? And why does it still produce measurable redshift? And what is the Big Bang, if it is not an explosion in a room? And why does the name persist anyway? Each question has a technical answer, but the answers change the meaning of the words, and that is why the paradox feels slippery. This chapter sets the mystery in its cleanest form before we reach for equations. The universe expands, and the expansion is measurable, written into spectra and background radiation. The expansion does not pick a center, and it does not require an edge, even if our minds keep sketching one. The expansion is not debris flying outward, but space-time evolving everywhere, with distances defined by a changing metric. The word nothing hides multiple concepts that must be separated, or the sentence will keep misleading us. From here, the path forward is not to imagine a better explosion, with a clearer boundary and a more dramatic outward rush. The path forward is to learn the geometry that makes intrinsic expansion possible, and to see how the mathematics protects us from our own metaphors. We will follow the evidence from redshift to the idea of a scale factor, and we will connect that factor to what we mean by distance. We will see how relativity replaces the stage with a dynamic fabric, and how that fabric can evolve without needing an outside. And we'll discover that dissolving this paradox opens the door to deeper ones, because every solved confusion reveals a sharper question. The question is not what lies outside the universe, as if outside were an address we could reach. The question is what we mean by outside, when space itself is the thing changing, and when our language was built for rooms. In the next chapter, we step from metaphor to mathematics, and we ask how distance is defined in an expanding cosmos. We will keep the balloon in the back of our minds, but we will listen more closely to the geometry it was trying to show us. The paradox from chapter 1 survives because we keep picturing space as a container, like a box with walls. We imagine a room, then ask what surrounds the room, then call that surrounding nothing, as if nothing were a kind of hidden substance. Modern cosmology starts by rejecting that stage picture, because the stage is part of the play, and the play can reshape it. When we say space, we often mean an emptiness where objects can be placed, measured, and moved around. In everyday life, that assumption feels harmless, because our bodies and tools never notice the deeper rules underneath. Yet the universe does not promise a fixed arena, and the evidence keeps hinting at something stranger, especially once we look beyond our immediate neighbourhood. If the arena itself can change, then the old question what is outside may be a grammar trap, not a scientific mystery. Newton's universe begins with absolute space and absolute time, and those words were meant literally. Space is a fixed grid that exists whether matter shows up or not, like graph paper laid down before anything is drawn. Time is a universal clock that ticks the same everywhere, independent of motion or location, and every observer is supposed to agree on its rhythm. In that framework, gravity is a force that reaches across emptiness, pulling masses through an unchanged arena. This Newtonian picture did not arise from laziness, and it was not an arbitrary philosophical choice. It grew out of a spectacularly successful program of prediction, from falling apples to planetary orbits to the return of comets. Absolute space gave Newton a stable reference for inertia, and absolute time gave him a common parameter for motion across the solar system. The universe became a vast, silent coordinate system, and physics became the art of describing trajectories inside it. That picture fits daily life because our measurements are local and slow, and because gravity is weak in our neighbourhood. A thrown ball never approaches the speed of light, and a kitchen clock never drifts because of a black hole. Our rulers seem rigid, our seconds feel universal, and the world behaves as though the stage were permanent. It also fits the grammar of moving into and spreading out, because there is always an external reference waiting in the background, but it quietly assumes a background that never responds, and nature does not keep that promise. When mass and energy concentrate, the universe does not merely place them onto a grid, as if pinning insects to a board. Instead, the grid itself becomes part of the interaction, and the meaning of distance becomes negotiable in a precise, measurable way. The deeper question is not only where matter goes, but what "where" even means. Einstein's general relativity replaces the background with a dynamical space-time, and that shift is more radical than it first sounds. Space and time are not separate containers, and they are not fixed in advance like a pre-printed map. The geometry can curve, stretch, and evolve, and matter and energy help determine how it does so. Gravity becomes geometry, meaning free fall follows the straightest possible paths in curved space-time. A useful way to picture this, without turning it into a cartoon, is to imagine that geometry is a set of rules. Those rules tell clocks how to tick, rulers how to span, and light beams how to travel through each local patch. When the rules change, the same coordinate labels can describe a different physical reality, even if the ink on the page looks identical. The universe, in this view, is not happening inside geometry. The universe is partly made of geometry. This is not a poetic rebranding of the same old force, and it is not merely a new metaphor for attraction. In relativity, you do not start with a rigid stage and add gravity on top like a special effect. You start with a metric, a rule, that turns coordinate differences into measured distances and times. Change the metric and you change what rulers and clocks mean, even if the coordinates look unchanged. The metric is not an optional decoration, and it is not a matter of taste. It is the mathematical object that encodes the local structure of space-time, including the light cones that define which events can influence which. If the metric tilts or stretches, the causal structure can shift in subtle ways, and the paths of particles respond with no need for a pulling hand. In plain language, geometry tells matter how to move, and matter tells geometry how to bend. Coordinates, in this framework, are labels, not physical rods painted onto reality. You can choose different coordinate systems, and the physics does not care, because the underlying relationships remain. What matters are invariant statements, like the proper time along a world line, or the proper distance between events on a chosen slice. The universe can look like it is doing different things in different coordinates, while the measurable content stays the same. This freedom is powerful, but it can also be disorienting. A coordinate grid can be stretched, twisted, or accelerated, and the symbols on the page will dutifully follow along. If we confuse the grid for the world, we will mistake a choice of description for a physical effect, and we will argue about ghosts. Relativity forces a discipline. Trust what can be measured, not what a diagram seems to suggest. This is where the phrase "expanding into" begins to fail, because into assumes an external place that already exists. It smuggles in the image of a larger room waiting beyond the walls, like a warehouse around a growing balloon. General relativity does not require any larger room, because the geometry that defines distance is already inside the model. Expansion can be an internal change in the metric, not motion through a pre-existing void. To rebuild intuition, separate two ideas that sound similar, even though they behave differently. One is objects moving through space, like cars separating on a highway while the asphalt stays put. The other is the distance rule changing, like the highway itself being rescaled between mile markers, while the cars keep their lanes. In cosmology, the second idea is the one that matches the data on the larger scales. The difference is subtle, and it matters because it changes what we think we're seeing. If galaxies are flying away, then we expect a centre, a blast, and a surrounding emptiness. If distances are being rescaled, then every place participates, and the question of an outside loses its grip. The same word, expansion, can describe two different movies, and only one fits the equations. Metric expansion means the proper distance between co-moving points grows with time, even if those points keep the same coordinate addresses. Co-moving points are defined to ride with the average cosmic flow, a statistical rest frame defined by the large-scale distribution of matter. They are not pushed by rockets, and they are not necessarily moving locally at high speed. Their separation increases because the metric changes, not because they are shrapnel from a central blast. Visually, imagine a faint grid drawn across a dark void, with galaxies pinned to intersections like beads on invisible threads. As time passes, the grid squares widen, and the beads remain at the same grid coordinates. Nothing needs to push the beads through space, because the definition of distance between grid lines is what is changing. The motion is in the ruler, not in the beads. This difference matters because it changes what we mean by recession speed, and it changes what speed is allowed to mean. In everyday life, speed is a local comparison of positions in a fixed space, measured by a single observer with a single clock. In an expanding universe, the rate of change of proper distance can include a contribution from the changing metric itself. That contribution is not a local velocity through space, and it is why the language of flying away misleads. The clean way to say it is that galaxies are often approximately co-moving on large scales, even though they are not perfectly at rest. Locally, gravity binds stars into galaxies and galaxies into groups, and those bound systems do not expand with the Hubble flow. The Milky Way does not stretch, and neither does the solar system, because local gravitational and electromagnetic forces dominate. But between distant, unbound regions, the cosmic expansion dominates the bookkeeping, and the large-scale map grows. That word bookkeeping is doing important work here, because cosmology is partly about choosing the right accounting system. We want a description that tracks what is stable, what is changing, and what is merely a coordinate artifact. Co-moving coordinates are designed to make the cosmic flow simple, even if local motions remain complicated. They let us separate the smooth expansion from the smaller ripples of peculiar velocity. Historically, this shift in thinking was not immediate, and it did not feel inevitable to the people living through it. Einstein's equations allowed dynamic solutions, but Einstein initially preferred a static cosmos, in part because the night sky looked eternal. He introduced a cosmological constant to hold the universe still, because the idea of global change felt implausible and philosophically unsettling. The mathematics was ready for expansion, but the intuition lagged behind. Meanwhile, other minds were already exploring what the equations implied, even when the implications seemed outrageous. Alexander Friedmann found solutions in which the universe expands or contracts, and Georges Lemaire connected those solutions to astronomical observations. Their work suggested that cosmic geometry could evolve like a living thing, with a history rather than a fixed identity. The stage, in their hands, became a dynamical actor. Then the observations and the mathematics converged, and the static option became harder to defend. The observational clue is still the same one that started the modern story, and it arrives through the thin, precise language of spectra. Distant galaxies show redshifted spectral lines, and the redshift correlates with distance across vast surveys. The simplest first interpretation is Doppler recession, like a siren dropping in pitch as it moves away. In the early 20th century, those spectra were not just data points, but fingerprints. Each element leaves a characteristic pattern of absorption or emission lines, like a barcode stamped into starlight. When those barcodes slide toward longer wavelengths, we call it redshift, because visible light shifts toward the red end of the spectrum. The shift is measurable with astonishing precision, even when the galaxy itself is a faint smudge. But the cosmological interpretation is deeper, because the same redshift can arise from expanding space. In general relativity, light travels along null geodesics in a changing geometry, and null means the path is defined by the local speed of light. As the universe expands, the wavelength of a photon is stretched along with the space it traverses. That stretching produces cosmological redshift, which is not merely a Doppler effect from motion through static space. A useful mental image is a wave drawn on a rubber band, with crests and troughs marked in ink. If you pull the band gently, the distance between crests increases, even though the ink marks stay on the band. The photon is not slowing down, and it is not losing energy to friction because there is no medium. Instead, the geometry that defines the wave's wavelength is changing along the path. The photon's wavelength scales with the universe's expansion between emission and observation, and that scaling can be written compactly. If the scale factor today is larger than it was when the light was emitted, the wavelength we measure is larger by the same ratio. In practice, astronomers express this with the redshift parameter z, which encodes how much the universe has stretched since the light left its source. The redshift becomes a geometric record, not just a kinematic one. There is a quiet consequence hidden in that word stretched, and it is easy to miss on a first listen. A stretched wavelength means a lower photon energy, because energy is proportional to frequency, and frequency drops as wavelength rises. Cosmology does not treat that lost energy as heat dumped into space, because space is not a substance with a temperature reservoir. Instead, the change reflects that energy conservation, in its simplest global form, is not guaranteed in an evolving geometry. This does not mean Doppler shifts are unreal or irrelevant, because the universe is not perfectly smooth. Nearby galaxies can have peculiar velocities, meaning motion relative to the co-moving flow caused by local gravitational pulls. Those local motions add a Doppler component on top of the cosmological redshift, sometimes even producing blue shift. But at large distances, the expansion term dominates, and the redshift becomes a time capsule of the metric's evolution. The distinction matters observationally, because it affects how we interpret maps of the cosmos. If we treat all redshift as simple motion through space, we might misread the large-scale pattern as a conventional explosion. If we treat redshift as metric stretching, we can connect it to AT, the scale factor, and to the universe's energy content. The same measurement, interpreted carefully, becomes a probe of cosmic history. To describe that history, cosmology uses a highly symmetric model as a first approximation, not because symmetry is sacred, but because it is testable. The Friedman, Lemaitre, Robertson, Walker framework assumes homogeneity and isotropy on large scales, meaning the universe is statistically uniform when averaged over immense volumes. Homogeneity means the universe looks roughly the same at every location when averaged over huge regions. Isotropy means it looks roughly the same in every direction from a typical vantage point. These are not metaphysical declarations about perfection, and they do not deny the obvious drama of galaxies and voids. They are simplifying assumptions supported by surveys of galaxies and by the near uniformity of the cosmic microwave background. When we take a wide enough view, the clumps and filaments become fluctuations around a smooth mean. The universe is messy up close, but it becomes simple at the largest scales. Visually, this is where the camera can pull back until structure changes character. First we see bright spirals and dusty lanes, then clusters like embers, then filaments like faint smoke, and finally a statistical fog. At that distance, the universe stops looking like a collection of objects and starts looking like a field with small perturbations. The simplification is not denial, it is a change of scale. The cosmic microwave background in particular is a kind of visual whisper from the early universe. It fills the sky almost uniformly, with tiny temperature variations that encode primordial density differences. Those variations are small, parts in 100,000, yet they are rich with information. They tell us that on the larger scales, the cosmos is close enough to homogeneous and isotropic for FLRW to be a powerful starting point. Those tiny variations also carry a clue about motion, and it is almost eerie in its simplicity. The microwave background defines a natural rest frame, because an observer moving through it sees a dipole pattern, slightly hotter in the direction of motion, slightly cooler behind. When we correct for that dipole, the remaining sky becomes remarkably uniform, as if the universe is offering a preferred notion of comoving. It is not absolute space returning, but it is a practical cosmic reference. In the FLRW picture, the metric can be written so that the expansion is captured by a single function of time, and that function is the scale factor. The scale factor, often written as a t, tells us how the size of spatial slices changes as cosmic time advances. Comoving coordinates stay fixed for galaxies that follow the Hubble flow, while their proper distances grow in proportion to AT. The expansion is then a change in the metric scale, not a drift across a fixed grid. Think of co-moving coordinates as addresses in a city whose map is being uniformly enlarged. The street names and house numbers stay the same, but the physical distance between intersections increases. Proper distance is what you would measure with a chain of rulers laid down at a given cosmic time, assuming you could freeze the expansion for the measurement. In an expanding universe, the same pair of co-moving addresses corresponds to a larger proper distance later. This is where the distinction between co-moving coordinates and proper distance becomes essential, because it prevents a category error. Co-moving coordinates are chosen to ride with the average flow, so they hide the expansion in the coordinates themselves. Proper distance is tied to the metric, so it reveals what is physically changing. If we confuse the two, we will argue about whether the universe really expands when the observables already answer. Once you accept that, a strange statement becomes less strange, even though it still sounds like a paradox. Two sufficiently distant galaxies can have a recession rate greater than the speed of light, and the math will not blink. That sounds like it violates special relativity, which forbids objects from moving through space faster than light. But the key phrase is through space, because superluminal recession in cosmology is not a local speed. Special relativity applies locally in small regions where space-time is approximately flat, and where we can ignore curvature across the measurement. General relativity allows the global geometry to change, and it allows coordinate-dependent notions of speed over large separations. No galaxy outruns a nearby photon in its local neighbourhood, and no observer watches a neighbour break the light barrier. The faster-than-light recession arises from the integrated expansion of space between widely separated co-moving points. If that still feels slippery, notice what we are comparing when we say speed. We are taking a proper distance defined on a chosen cosmic time slice, then differentiating it with respect to cosmic time. That operation mixes geometry and time slicing, and it is not the same as a single object's velocity measured locally. The result can exceed c without violating the local speed limit, because the local speed limit is about nearby measurements. This is also why the Hubble law is not a simple velocity law in the everyday sense, even though it looks like one at first glance. The relation between recession rate and distance comes from the scale factor's time dependence and from how FLRW geometry assigns distances. It is a statement about how the metric evolves on a cosmic slice, not a report of engines firing. Treating it as shrapnel speed invites the wrong mental movie, with a centre and an outward blast. The centre problem is a language problem as much as a physics problem, and language is stubborn. In a homogeneous expansion, every co-moving observer sees others receding, and the pattern looks the same from many vantage points. That does not require a central location inside space, because the expansion is not an explosion into a surrounding emptiness. It follows from the rule that distances scale up everywhere, the way every point on a stretching grid sees separations increase. A vivid way to picture this is to imagine a nighttime city seen from above, with streetlights forming a rough lattice. Now imagine the entire map being smoothly enlarged, so every block lengthens in proportion. From any one streetlight, all the others drift away, and the farther ones drift faster, yet no streetlight is privileged as the centre. The centre is not missing, because the model never asked for one. The edge problem is similar, and it often arrives disguised as a childlike question that refuses to die. A finite universe can be unbounded, like the surface of a sphere has finite area without an edge. If you walk far enough on that surface, you do not fall off, and you do not encounter a boundary wall. A universe can also be spatially infinite, in which case there is no boundary to begin with. In both cases, expansion is defined internally by the metric, not by a boundary pushing into an exterior. The model does not need an outside coordinate to make sense of growth, because outside is not part of the geometry being described. What changes is the scale of distances within space, not the position of space within a larger container. The intuition of a surrounding void is an imported image, not a demanded feature. The word space in physics therefore means something more specific than emptiness, and that specificity is the point. It means the geometric structure that lets us define distances, angles, volumes, and the causal order of events. In relativity, that structure is not fixed, and it is not merely a passive backdrop. It can carry curvature, it can evolve, and it can influence the paths of matter and light. Curvature, here, is not a bend into a higher dimension that we must visualize as a rubber sheet. It is a statement about how geometry behaves when you compare nearby directions, triangles, and parallel lines. In curved space, The angles of a large triangle may not add to 180 degrees, and geodesics that start parallel may converge or diverge. These are measurable effects, and they can be encoded in the metric without invoking an external embedding space. You can even hear curvature in the language of navigation, because geodesics are the straight lines that geometry permits. On a plane, straight lines stay parallel, and the shortest path is familiar. On a sphere, great circles play that role, and two straight routes can meet even if they begin side by side. In space-time, the same idea governs how planets orbit, and how light bends near massive bodies. This is the core move that dissolves the grammar of into nothing, even if the feeling lingers. If space is the set of distance relations defined by the metric, then more space means those relations have changed. It does not mean the universe has invaded an external volume, like smoke filling a warehouse. It means the internal ruler of the cosmos has been rescaled by cosmic history. Still, there is a remaining discomfort that deserves to be named, because it is where many viewers get stuck. If coordinates are arbitrary, how do we talk about expansion as something real, rather than a trick of description? The answer is that expansion shows up in observables, not in coordinate choices, and observables do not care about our labels. Redshift, angular sizes, brightness relations, and the cosmic microwave background encode the scale factors change. Consider angular size, for example, which ties geometry to what we see on the sky. If you know an object's physical size, its apparent size depends on the distance rule between you and it. In an expanding universe, that distance rule evolves, and so the same kind of object can appear larger or smaller in ways that reveal the geometry. The expansion is not a trick of labels, because it leaves measurable fingerprints across independent methods. Brightness adds another layer, because light does not just travel, it dilutes in an expanding cosmos. Photons arrive less frequently because of time dilation, and each photon arrives with reduced energy because of redshift. The surface brightness of distant galaxies fades in a characteristic way, and that fading is part of the same geometric story. Even without touching the equations, the sky carries the signature of a changing scale factor. The role of light is central because light is what connects distant regions, carrying information across cosmic time. A photon emitted when the scale factor was smaller arrives with a longer wavelength, and that change is written into its colour. That stretching is cumulative along the photon's path, reflecting the universe's changing geometry. The redshift becomes a time machine, telling us how much the universe expanded during the photon's journey. Visually, imagine a single photon leaving a young galaxy, a thin thread of light crossing a darkening universe. Along the way, the grid of space subtly widens, and the photon's wave crests spread farther apart. By the time it reaches our detectors, the same photon is gentler, redder, and less energetic. We do not see the expansion directly, but we see its imprint in the light's stretched rhythm. This also reframes the Big Bang story in a way that fits the geometry, and it changes what beginning means. The Big Bang is not matter rushing into pre-existing darkness, as if the universe were a fireball thrown into empty space. It is a hot, dense early state in which the scale factor was much smaller, and the universe was evolving rapidly everywhere. When we run the model backward, we do not converge on a location in space. Instead, we converge on a limit in time where densities and curvatures grow, and our current physics approaches its boundary. The equations point toward an early regime where quantum effects of gravity may matter, and where classical spacetime may no longer be the right language. That boundary is not a wall in space, but a sign that our description has reached the edge of its validity. The mystery is not where did it happen, but what rules apply there. At this point, the central question tightens rather than disappears, because geometry raises as many questions as it answers. If expansion is the evolution of the metric, what determines that evolution, and what fixes the pace? What sets the rate at which the scale factor changes, and why did it change differently in different eras? The stage is not a stage, but it still follows rules, and those rules can be written. In Einstein's theory, those rules are encoded in field equations that relate curvature to energy and momentum. The content of the universe, matter, radiation, and whatever else exists, acts like a source for geometry. Geometry, in turn, governs how that content moves and how light propagates. The feedback is continuous, and it is local, even though its consequences can be global. There is something almost unsettling about that reciprocity, because it denies us a fixed foundation. In Newton's world, space and time are the silent referees, and matter plays the game. In Einstein's world, the referees can be pushed, and the field itself can ripple, carrying gravitational waves across the cosmos. The universe is not set on a stage. It is a coupled system whose where and when participate. Here the documentary shifts from language to dynamics, because definitions alone do not predict a universe. We have defined what space means in modern cosmology, and we have separated motion through space from expansion of space. We have introduced co-moving coordinates, proper distance, and the idea that superluminal recession is not a local violation of relativity. We have connected redshift to stretched wavelengths, not only to Doppler motion. Now we need the governing equations that turn these ideas into predictions, and we need them in a form that matches the symmetries we observe. In the Flabiu framework, the scale factor becomes the central character, and its time evolution encodes the universe's history. The next step is to see what drives AT, and how matter, radiation, curvature, and dark energy enter the story. If the universe does not expand into an outside, then the real question becomes what makes the inside geometry grow. Transition. If space is dynamic, then expansion is not a metaphor and it demands a mechanism. Transition. To answer what governs growth, we follow the scale factor into the Friedmann equations. Expansion survives because it is not a mood or a metaphor, and it is not a story we tell ourselves to feel oriented. It is an inference forced by light, calibrated distances, and early universe chemistry, three kinds of evidence that do not need each other to exist. When they agree anyway, the agreement becomes difficult to dismiss as coincidence or fashion. We start with the simplest clue, a pattern that repeats across the sky with stubborn consistency. Galaxies carry spectral fingerprints, and those fingerprints slide toward longer wavelengths, as if the universe has quietly leaned away. On screen, the effect is almost modest, thin dark lines like barcodes, drifting redward by fractions of a nanometer. Yet those tiny shifts accumulate into a cosmic statement. Redshift is not a colour impression, and it is not a poetic reddening like a sunset. It is a measurable displacement of known atomic lines, recorded with spectrographs that split light into precise wavelengths. Hydrogen, calcium, oxygen, and iron each mark the spectrum with characteristic absorption features. When those features appear where they should not be, the discrepancy is numerical and repeatable. A spectrograph turns a telescope into a kind of chemical and kinematic instrument, and it does so with ruthless clarity. Light enters a narrow slit, spreads through a prism or diffraction grating, and lands on a detector as a calibrated spectrum. The calibration itself is meticulous, anchored by laboratory lamps and reference lines measured on Earth. In practice, astronomers cross-correlate observed spectra with templates, extracting redshift even when lines are faint. The result is a dimensionless number, Z, that can be compared across objects and surveys. In the 1910s and 1920s, the raw ingredients of the discovery arrived in pieces, and they arrived with uncertainty attached. Vesto Slipher measured large redshifts for spiral nebulae, hinting that these objects were moving fast. At the time, even the nature of those spirals was disputed, and the great debate still echoed in observatory halls. Then Edwin Hubble assembled distances to nearby galaxies and compared them to their redshifts. Georges Lemaitre had already framed the same relation theoretically, using general relativity to connect a dynamic universe to observed recession. The result became the Hubble-Lemaitre law, and its simplicity is part of its power. Recession velocity is proportional to distance, so farther galaxies recede faster in a near-linear trend. On a plot, points rise like a slanted band, imperfect but unmistakable. The slope is the expansion rate, and the scatter carries information about local gravitational tugs. That proportionality is not a single data point, and it is not a fragile line drawn through a handful of galaxies. It is a statistical law that strengthens as surveys expand, and it persists across independent catalogues taken with different instruments. When modern surveys measure millions of redshifts, the relation becomes a backbone rather than a curiosity. The universe, averaged over large scales, behaves as though distances between unbound regions are increasing. At first, the law sounds like an explosion into empty space, a blast with a centre and an edge. Relativity changes the interpretation, because recession can reflect expanding geometry between co-moving regions rather than motion through pre-existing emptiness. In general relativity, space and time are not a stage separate from actors. The metric itself can evolve, and that evolution can carry galaxies apart without giving them a special central origin. In an expanding metric, a photon's wavelength stretches while it travels, and the stretching is built into the geometry. The redshift parameter z encodes the ratio of the universe's scale then and now. A galaxy observed at z⁻1 is seen when the scale factor was about half today's value. The light did not merely travel far, it travelled through a universe that changed while it was en route. Redshift alone does not give a distance, because the conversion depends on the expansion history. To turn redshifts into an expansion curve, cosmology needs a reliable way to measure how far away things are. That requirement sounds mundane, yet it is where the craft of observational astronomy becomes crucial. Distance is the hidden variable that turns a spectral shift into a cosmic timeline. That is the cosmic distance ladder, built from overlapping methods that calibrate one another across increasing ranges. Each rung extends reach, but each rung must be anchored to something closer and better understood. The ladder is not one technique, and it is not one instrument. It is a chain of inference, and the chain must not slip. The first rung is parallax, the shift of a nearby star against a distant background as Earth orbits the Sun. Geometry gives distance directly, but only for nearby stars because the angles are tiny. A star 1 parsec away shifts by 1 arc-second, about the width of a coin seen from kilometers away. Modern astrometry missions, especially Gaia, measure micro-arc-seconds, angles so small they feel like a mathematical abstraction. In visuals, the star field becomes a fixed tapestry, while one point traces a barely perceptible ellipse. Parallax calibrates standard candles inside the Milky Way, objects whose intrinsic luminosity can be inferred. The key early candle is the Cepheid variable, whose pulsation period correlates with intrinsic luminosity. Cepheids brighten and dim because their outer layers expand and contract, driven by changes in opacity. The physics is not mystical, it is a heat engine in a star's envelope. When helium in the outer layers becomes partially ionized, it traps heat, builds pressure, and forces the star to swell. Then it cools, becomes more transparent, and falls back. Henrietta Leavitt discovered the period luminosity relation while studying Cepheids in the Magellanic Clouds. Those stars were effectively at a common distance, so differences in apparent brightness reflected real differences in luminosity. Her insight turned a flicker into a ruler, and the ruler could be carried beyond the Milky Way. Measure a Cepheid's period, infer its true brightness, then compare it to what the telescope records. Compare true brightness to observed brightness, and distance follows by inverse square dimming, a simple law with profound reach. Twice as far means 4 times fainter, provided dust and calibration are controlled. Cepheids then calibrate distances to nearby galaxies that host them, and those galaxies become stepping stones. The ladder works because each rung overlaps the next, creating cross-checks rather than isolated claims. The process is careful because stars are not identical light bulbs, and the universe does not volunteer clean laboratory conditions. Cepheid luminosities depend subtly on metallicity, and dust can redden and dim their light in ways that mimic distance. Astronomers observe in multiple bands, model extinction, and apply corrections based on stellar populations. In vivid visual terms, the ladder is built in the glare of real astrophysical messiness. The achievement is not that it is perfect, but that uncertainties can be quantified. Farther out, Type Ia supernovae extend the ladder into deep space. They are thermonuclear explosions of white dwarfs that reach a characteristic peak luminosity after calibration. In the standard picture, a carbon-oxygen white dwarf approaches instability, ignites runaway fusion, and unbinds in seconds. The blast synthesizes nickel-56, whose radioactive decay powers the light curve for weeks. On screen, the supernova flares like a brief second sun, then fades as the decay chain quietly keeps time. Type Ia supernovae are not perfectly identical, and that imperfection is a feature to be managed. Light curve shape and color corrections standardize them, tightening scatter and enabling precision cosmology. A slower declining supernova is typically brighter, and empirical relations capture that trend. Observers also correct for host galaxy properties, because environment can subtly influence the explosion's observed behavior. With supernova distances, redshift becomes a timeline rather than a mere velocity proxy. We can reconstruct how the scale factor changed, not just that it changed. Each supernova is a point on a Hubble diagram, a plot of distance versus redshift. The curve of that diagram carries the imprint of cosmic deceleration and acceleration. Redshift surveys then map the expanding cosmos in 3 dimensions, transforming the sky into a volume. Each galaxy contributes an angle on the sky and a redshift that approximates distance once a cosmology is assumed. On screen, dots become filaments, and filaments braid into walls around dark voids. The cosmic web emerges as a kind of architecture, delicate yet immense. It is not random clutter. It resembles a frost pattern spreading across a window, guided by gravity's quiet preference for clumping. The map reveals structure, but also the Hubble flow underneath it. On large scales, the recession pattern dominates over local peculiar velocities, which are the deviations from pure expansion. Peculiar velocities arise because gravity pulls matter into overdense regions, creating coherent flows. In a nearby cluster, galaxies can orbit at thousands of kilometers per second, yet the cluster as a whole still rides the expanding background. Local motions still matter, and they keep the story honest. Nearby galaxies can be blue-shifted if gravity pulls them toward us, as in the Andromeda system. The local group is a gravitationally bound island, and its internal dynamics do not obey the Hubble flow. This is a reminder that expansion is not a universal push acting on everything equally. Yet beyond the local group, the expansion signal overwhelms the noise, and the statistical pattern returns. The universe behaves like a stretching metric with small velocity perturbations layered on top. In practice, astronomers average over many galaxies to recover the underlying trend. The more sky we measure, the clearer the large-scale behavior becomes. This is the first independent pillar. Distance indicators plus redshifts imply a universe whose large-scale separations grow with time. The inference is geometric, not psychological, and it is anchored in repeated measurements. Even if we knew nothing about the early universe, the nearby cosmos would still whisper expansion through its spectra. The second pillar comes from a glow that does not belong to any galaxy, and it is visible in every direction. It is the cosmic microwave background, faint radiation filling the entire sky. If the universe has a memory, this is part of it, a leftover bath of photons that predates stars. In visuals, the sky becomes a smooth, cold fog, then resolves into a map of tiny mottled variations. The CMB was predicted as a relic of a hot early universe, then discovered in 1965 by Arno Penzias and Robert Wilson. They detected a persistent microwave hiss that would not vanish, no matter how they adjusted their antenna or cleaned away suspected sources. The signal was isotropic, the same from every direction, which made local explanations awkward. Its very blandness was the clue, because a true cosmic background should not care where Earth happens to be. The key fact is its spectrum, because the spectrum is hard to counterfeit. The CMB is an almost perfect blackbody, meaning it matches thermal radiation from matter once in equilibrium. A blackbody curve is not just smooth, it has a specific shape fixed by temperature. When the COBE satellite measured that curve, the residuals were astonishingly small. The fit was so precise that it ruled out many alternative origins that would have left distortions, bumps, or frequency-dependent scars. Its temperature today is about 2.725 Kelvin, a number that sounds like trivia until you realize how it is obtained. Instruments compare intensities at multiple frequencies and fit them to Planck's law with exquisite precision. The result is a thermodynamic statement about the whole sky. It is as if the universe itself carries a calibrated thermometer reading. A blackbody at 2.725 K implies a hotter past, because expansion cools radiation. In an expanding universe, radiation cools as wavelengths stretch, so temperature scales with the inverse scale factor. Double the scale factor, and the photon wavelengths double, shifting microwave photons toward even longer radio waves. The cooling is not due to photons getting tired, but due to geometry changing their wavelengths. Run that scaling backward, and the universe becomes dense and hot, and the words stop being metaphorical. At early times, photons scattered constantly off free electrons in an ionized plasma, a state where atoms could not hold together. The mean free path of a photon was tiny, so the universe was opaque like the interior of a star. Light existed, but it could not travel far. Around 380,000 years after the Big Bang, the universe cooled enough for electrons and protons to form neutral hydrogen. This epoch is called recombination, though it is really the first stable combination. As electrons bound into atoms, the scattering rate dropped dramatically. Photons then decoupled and streamed freely, beginning a journey that ends in our detectors. That release is the CMB, a fossil snapshot of the last scattering surface. We do not see a boundary in space, we see a boundary in time, because we look back along our past light cone. Every direction points to a different patch of that ancient plasma, all at roughly the same cosmic age. The sky becomes a time machine that requires no exotic technology. The CMB is nearly uniform, which already tells us something profound. It suggests the early universe was remarkably homogeneous on large scales, with temperature variations of only tens of microkelvin. Yet it is not perfectly uniform, and those tiny anisotropies are the seeds of everything later. On a full sky map, the mottling looks like gentle speckle, but it encodes a detailed physical record. Some of the anisotropy is a simple dipole caused by our motion relative to the CMB rest frame. Subtract that motion, and the remaining pattern is primordial. Tiny hot and cold spots correspond to slight over and under densities in the early plasma. Gravity tried to compress these regions while radiation pressure resisted, setting up acoustic oscillations. Those oscillations leave a characteristic angular pattern, a series of peaks in the power spectrum. The position of the first peak tells us about spatial geometry, because geometry determines how physical scales project onto the sky. The relative heights of peaks reveal the baryon content, because baryons add inertia to the oscillating plasma. Even the damping tail at small scales carries information about diffusion, the smoothing of fluctuations by photon random walks. The CMB therefore does two jobs at once, and it does them with a single dataset. It confirms a hot, dense past, and it constrains how quickly the universe expanded before stars existed. It also ties together matter, radiation, and the initial conditions that later grew into structure. The early universe becomes a laboratory where physics leaves imprints on a cosmic screen. This is the second independent pillar. Even without galaxies, the sky carries a thermal relic that only makes sense in an expanding, cooling cosmos. The blackbody spectrum is the kind of evidence that resists reinterpretation. If the universe were not once hot and dense, why would the sky glow like a perfect thermal cavity? The third pillar is older than any light we can see directly, because it is written into the composition of matter itself. It is the primordial abundance of the light elements, forged when the universe was minutes old. This is chemistry under extreme conditions, when the cosmos was hot enough to run nuclear reactions everywhere. In visuals, the scene shifts from star fields to a stylized early universe, dense, bright, and rapidly cooling. Big Bang nucleosynthesis begins when the universe is hot enough for nuclear reactions, but cool enough for deuterium to survive. That balance is controlled by expansion, because expansion sets the clock. At very high temperatures, deuterium is photodissociated as soon as it forms, a bottleneck sometimes called the deuterium barrier. When the temperature falls enough, deuterium can persist and fusion can proceed. If expansion is too fast, reactions freeze out early, leaving less time to build helium and other nuclei. If expansion is too slow, more neutrons decay and more fusion proceeds, changing final abundances in a predictable way. Neutrons are slightly heavier than protons, and free neutrons decay with a half-life of about 10 minutes. The neutron-to-proton ratio therefore evolves while the universe cools. The theory predicts a universe dominated by hydrogen, with about a quarter of the mass in helium-4. It also predicts trace deuterium, helium-3, and lithium-7, each sensitive to conditions in different ways. Helium-4 is robust because it is tightly bound, so once deuterium survives, helium forms efficiently. Deuterium is fragile, so its abundance is a particularly sharp probe of baryon density. But here's the part that should make you skeptical. A prediction is worthless if you can't test it, and these elements were forged more than 13 billion years ago, in a fire no telescope can see. So how do you check the recipe of a universe that's only minutes old? It turns out there are places in the cosmos that never got the memo about cosmic evolution. Cosmic time capsules, hiding in plain sight, and one of them holds a number so precise, it nearly settled a decades-long argument about what the universe is made of. We'll crack that capsule open later in this video. Stay with us, because that's going to blow your mind. Astronomers test these predictions in environments that preserve early chemistry as cleanly as possible. Deuterium in pristine gas clouds is especially sensitive to the baryon density, and it is measured through absorption lines in the spectra of distant quasars. The technique is delicate because deuterium lines sit close to hydrogen lines, and contamination must be ruled out. When the measurements work, they provide a window into the universe when it was still simple. Helium is measured in low metallicity regions where stellar processing is minimal, such as certain dwarf galaxies and H2 regions. Observers analyze emission lines from ionized gas, modeling temperature, density, and radiative transfer. The goal is to infer what helium fraction existed before stars enriched the gas. Lithium is measured in old stars, though the lithium story remains complicated and is still debated. The broad agreement is striking, and it is not merely qualitative. A single expanding universe model can match the CMB baryon density and the deuterium abundance with consistent parameters. That consistency links minutes-old nuclear physics to 380,000-year-old photon decoupling. It is the same universe, described by the same expansion, leaving independent traces. This is the third independent pillar. Early universe nuclear chemistry depends on the expansion rate, and the observed element ratios match that dependence. The success is not that every detail is settled, but that the overarching framework works across radically different epochs. When chemistry and radiation both point to expansion, the inference gains weight. 3 lines of evidence now converge, and they converge with different instruments and different vulnerabilities. Redshifts plus distances show expansion directly in the nearby and intermediate universe. The CMB shows cooling from a hot past, encoded in a near-perfect blackbody spectrum and a patterned anisotropy field. Nucleosynthesis shows timed reactions in a rapidly changing early universe, preserved in elemental abundances. Expansion is therefore not a philosophical preference, and it is not a conclusion reached by aesthetic taste. It is the simplest framework that explains multiple datasets that do not share the same systematics. Distance ladders worry about dust and calibration, while the CMB worries about foreground subtraction and instrument stability. Element abundances worry about astrophysical processing, yet the same expansion story survives each test. But the evidence does more than say the universe expands, because it also tells us the expansion follows rules that change with cosmic time. The universe does not expand like a clockwork mechanism with a fixed speed. Its rate responds to what the universe contains. In that response, we find both clarity and mystery. To see that, we track the expansion rate, often written as h of time, which is the fractional growth rate of the scale factor, which is not constant in most models, because the dominant energy components evolve as the universe grows. The Friedmann equations translate energy density and pressure into expansion behavior. In plain language, what fills the universe influences how fast it can stretch. In the early universe, radiation mattered most, and it mattered in a way that feels counterintuitive. Radiation energy density drops quickly as the universe expands, because photons redshift and dilute. The number density falls with volume, and each photon loses energy as its wavelength stretches. That double effect makes radiation fade rapidly as the universe grows. As the universe expanded and cooled, matter took over as the dominant component. Matter density also dilutes with volume, but it does not lose energy to redshift in the same way. A particle's rest mass remains, even as space expands around it. This difference is why the universe transitions from radiation domination to matter domination at a particular epoch. Radiation and matter both slow expansion through gravity, because positive energy density contributes to gravitational attraction. In a matter or radiation-dominated era, the expansion decelerates, meaning the scale factor grows but the rate decreases. The universe still expands, yet it does so under a kind of gravitational braking. This deceleration is not a guess. It is the behavior predicted by general relativity for ordinary components. Then a late-time change appears in the supernova data, and it arrives as a subtle bend in the Hubble diagram. Distant type Y supernovae look dimmer than expected in a purely decelerating universe. Dimmer means farther at a given redshift, once corrections are applied and selection effects are modelled. Farther implies the universe expanded more than a decelerating model predicts during the light's travel time. The inference is late-time acceleration, a conclusion that initially felt almost perverse. Something like dark energy, or a cosmological constant drives expansion to speed up rather than slow down. In the equations, this corresponds to an energy component with negative pressure, which changes how gravity acts on large scales. In plain language, the universe has a term that behaves like a repulsive contribution to the expansion dynamics. Historically, the cosmological constant has a complicated reputation, appearing in Einstein's equations and later being reconsidered. What matters here is not the biography of the symbol, but the observational need for something with similar effects. The supernova result was not accepted because it was dramatic, but because it survived scrutiny. Independent teams, different telescopes, and improved datasets kept pointing the same way. This is not a single-team claim, and it is not supported by supernovae alone. Supernovae, baryon-acoustic oscillations, and the CMB together support a universe with matter plus a dark energy-like component. Baryon-acoustic oscillations provide a standard ruler, a preferred clustering scale imprinted by early universe sound waves. When that ruler is measured at different redshifts, it traces the expansion history in another independent way. Acceleration deepens the central question, because it adds a turning point to the cosmic narrative. If expansion is geometry evolving, why did geometry switch from decelerating to accelerating? Was dark energy always there, waiting to dominate as matter diluted, or does it change with time? The evidence demands acceleration, yet it also invites doubt about what the underlying component truly is. The story becomes more precise when we separate two ideas that are often conflated in casual conversation. The scale factor describes overall stretching, while local structures can remain bound and non-expanding. A galaxy cluster can be held together by gravity, even as the space between clusters grows. The universe expands, but it does not require every object to swell. Galaxies and solar systems do not grow with the Hubble flow, because electromagnetic forces and local gravity dominate at those scales. Atoms are not being tugged apart by expansion, and planetary orbits are not quietly inflating. Expansion is a large-scale property of the metric, most cleanly defined for separations between unbound regions that follow the general flow. This distinction keeps the concept from becoming a caricature. That separation prevents a common mistake, and it matters for intuition. Expansion is not a force pulling atoms apart, it is a rule for distances between regions not held together by binding energy. When we say space expands, we mean the relationship between comoving coordinates changes with time. The language is imperfect, but the mathematics is precise. Now the modern cliffhanger arrives, because precision has created disagreement where we expected convergence. Different methods infer different values for the present expansion rate, h0, and the difference is not trivial. The disagreement is small in absolute terms, yet large compared to the quoted uncertainties. In a field built on careful error budgets, that mismatch is unsettling. It raises a quiet question. When the universe speaks in numbers, are we hearing an accent we do not yet understand? One approach is the local distance ladder, which stays close to the present universe. Calibrate Cepheids and other standard candles, measure supernova distances, then infer H0 from nearby expansion. This method depends on photometric calibration, dust corrections, and the integrity of each rung. It is observationally direct, but it is also a chain, and chains can hide weak links. Even small issues, crowding in galaxy images, subtle detector nonlinearity, or population differences can shift the final slope. Another approach is early universe inference, which begins with the CMB. Fit the CMB anisotropy pattern with a cosmological model, then extrapolate forward to predict H0 today. This method is powerful because the CMB data are rich, and the model is tightly constrained. Yet, it is also model-dependent, meaning the inferred H0 is not measured directly but derived through a framework. The procedure is elegant, but it assumes the same physics connects recombination to the present, without hidden additions. These two values do not match within quoted uncertainties, and the mismatch has persisted as measurements improved. The mismatch is called the Hubble tension, and it has become a focal point because it may indicate something real. If the methods were simply noisy, better data would bring them together. Instead, the gap has remained. If the tension is real, it hints at missing physics, and the possibilities are both exciting and constrained. It could mean new early universe components that change the sound horizon scale. It could mean altered dark energy behavior that affects late-time expansion, or it could mean subtle measurement systematics that masquerade as new physics. If the tension is systematic, it still matters, because it would reveal a hidden bias at the percent level. It would mean our calibration chain or our modelling assumptions contain an error that is small but consequential. Precision cosmology lives in that regime, where a few percent can rewrite conclusions. The tension forces the community to interrogate every step, from detector linearity to stellar population modelling. Either way, the tension reframes certainty without erasing it. Expansion is not in doubt, but the exact expansion rate and its detailed history remain contested. The universe is expanding, yet it refuses to be fully pinned down by one clean number. That refusal is not failure, it is the frontier. That is the chapter's turning point, and it changes how the evidence feels. Evidence makes expansion unavoidable, yet the universe keeps a margin of ambiguity where new insight might enter. The clues are strong, but they are not the final word. In science, that combination is often where the deepest progress begins. We return to the paradox with sharper tools, because the evidence has disciplined our imagination. If expansion is measured internally, then the question is not what space expands into. The question becomes what the universe's geometry is, and how that geometry is shaped by its contents. The language shifts from outside to curvature, from edge to global structure. Is space flat, closed, or open? And what does that mean without an outside? In a closed geometry, you can travel far enough in one direction and return, without ever encountering a boundary. In an open geometry, space extends without wrapping, yet it still need not have an edge. Flatness, too, is a geometric statement about angles and triangles, not about emptiness beyond a wall. The unsettling part is that geometry can be globally simple, while remaining observationally elusive, because we only see one horizon-limited patch. The evidence tells us the universe expands, and it tells us the expansion changed character over time. The next step is to ask what shape can expand without an edge, and what horizons limit what we can ever observe. When we look outward, we look backward, and the observable universe becomes a finite region even if the whole is not. The deeper puzzle is not merely size, but definition, transition. The clues in light establish expansion as a measured fact, not a philosophical claim. Transition. Now we confront the deeper puzzle of global shape, horizons, and whether an outside is even defined. Imagine standing at the edge of everything, then realizing there is no edge at all, no rim, no fence, not even a faint boundary line to lean against. The question of expansion changes the moment the universe is not treated like a container, because containers imply walls and an outside. The central question remains, but it becomes sharper and more technical. What does it mean for space to expand, without expanding into an external nothing, and without smuggling in an invisible backdrop? Picture the usual mental image: an explosion in darkness, debris flying outward, a center left behind like a scar. That picture is powerful because it matches ordinary experience, and because our verbs quietly import a stage. Outward assumes an outside, and from assumes a privileged starting point. Yet in modern cosmology, the universe is not modelled as stuff moving through a pre-existing void. Space itself is part of what is being described, and that shift removes the stage beneath the actors. When the stage is dynamical, even the meaning of distance becomes a physical variable rather than a passive measuring stick. The first trap is the phrase, "center of the universe," because it suggests a special location where expansion began and where the geometry is anchored. In an FLRW universe, the expansion is homogeneous and isotropic on large scales, meaning it looks statistically the same everywhere and in every direction. That symmetry is not a philosophical preference, and it is not a poetic simplification. It is a mathematical statement built into the metric, and it is supported by observations like the near uniformity of the cosmic microwave background. In practice, the FLRW line element encodes this with a single scale factor multiplying space, as if the universe carries one global stretch setting. When cosmologists say, statistically, they are admitting something subtle and important. The universe is not a perfect crystal, and it is not a featureless fog. It is a lumpy place, full of galaxies, clusters, and dark matter halos that pull and twist their neighbourhoods. Yet the FLRW model asserts that if you zoom out far enough, the lumps average out, and the large-scale rules become simple. That averaging scale is not a slogan. It is a practical statement about when the cosmic web becomes a background texture rather than the whole story. Homogeneity and isotropy do not claim the universe is perfectly smooth in detail. Galaxies cluster into filaments, voids, and walls, and gravity sculpts structure across billions of years. In deep surveys, those filaments look like threads of light stitched across blackness, while voids open like silent cavities between them. Yet when you average over sufficiently large volumes, the distribution becomes uniform enough that the FAR-W approximation works. The equations then refuse to single out a special point, and they refuse to grant any observer a privileged view of the global flow. The symmetry is not that every place is identical in detail, but that no place is singled out by the large-scale rules. From any typical galaxy, other galaxies recede on average, and the pattern is remarkably simple when plotted. The farther they are, the larger the recession rate appears, roughly proportional to distance. This is Hubble's law in its idealized form, and it is not merely a statement about motion. It is consistent with a single scale factor changing over time, stretching the distances between co-moving observers. That proportionality emerges because the same fractional expansion applies everywhere, so doubling the distance doubles the accumulated stretch. That proportionality has a clean visual rhythm when you imagine it as a grid. Every interval between neighbouring points grows, and the growth compounds across many intervals, so distant points separate faster. It is not that the far galaxies try harder to flee. It is that there is simply more expanding space between you and them. In this picture, recession speed is less like a rocket's thrust, and more like interest compounding across a longer span of time. When astronomers measure this recession, they do not watch galaxies drift across the sky like insects on a windshield. They measure redshift, light stretched to longer wavelengths as it travels through an expanding metric. The spectrum of a galaxy carries a barcode of atomic lines, and those lines shift in a way that encodes the expansion history. Hydrogen, calcium, and oxygen leave recognizable fingerprints, and the entire pattern slides toward red as the universe grows. The farther the galaxy, the longer the light has traveled, and the more the scale factor has changed during the journey. In careful analyses, astronomers separate this cosmological redshift from local Doppler shifts, and from gravitational redshift, because different physics can tint the same observation. This is why redshift is not just a number, and not just a colour shift. It is a time machine built into the sky, because looking far away is also looking far back. The light arriving at a telescope tonight began its trip when the universe was younger, denser, and arranged differently. Each photon carries a record of the metric it crossed, stretched gradually, step by the changing scale factor. Even the photon arrival rate is affected, so distant supernova light curves appear time-dilated, a subtle confirmation that expansion is written into spacetime itself. It is tempting to say galaxies are moving through space, and locally they do have peculiar velocities. Clusters fall together under gravity, and nearby galaxies can even approach each other, despite the overall expansion. The Andromeda Galaxy, for example, is on a collision course with the Milky Way, not because expansion has stopped, but because gravity dominates on that scale. Yet on the largest scales, the dominant effect is the expansion of the metric, and co-moving galaxies are at rest in those coordinates. The recession is not a blast wave from a point. It is the geometry of distance evolving everywhere at once. If you could freeze cosmic time and lay down rulers, the rulers would define a different separation tomorrow. There is a useful distinction here, and it is easy to miss in casual language. Peculiar velocity is motion through local space, the kind that can be measured by watching objects move relative to nearby neighbours. Cosmological recession is different, because it is tied to the stretching of the distance rule itself. In the FAR-W picture, co-moving observers keep the same spatial coordinates while their proper separation grows. That is why recession speeds can exceed the speed of light at great distances without violating relativity. No object locally outruns a light beam, but the metric can change the gap between them. The balloon analogy from earlier chapters was not about a literal surface floating in a room. It was about an intrinsic distance rule that changes everywhere at once, even if you never mention an outside. On the balloon surface, every point sees others moving away as the rubber stretches. Yet no point on the surface is the centre of the surface. The analogy is imperfect, but it is honest about what matters. The geometry on the surface, not the air around it. To make the visual concrete, imagine ink dots painted on the balloon, each dot representing a galaxy. As you inflate it, the dots separate, and each dot can draw the same conclusion. Everything is receding, and the farther dots recede faster. The crucial detail is that the dots are not sliding across rubber, as if pushed by a wind. The rubber itself is changing, and the distances measured along the surface increase. If the dots could measure the change with rulers made of the same rubber, they would face a deeper puzzle, because their rulers would stretch too. In cosmology, we avoid that trap by using physical standards like atomic transitions to define units that do not go soft with the expansion. The center exists only in the embedding space, which the surface does not need for its own geometry. A two-dimensional creature living on that surface could do physics without ever referencing the room around it. The surface geometry is complete without an external coordinate system, because all measurable quantities, angles, distances, areas, are defined internally. Cosmology makes the same move, but in 3 spatial dimensions, using a space-time metric rather than a sheet of rubber. The mathematics is intrinsic, and that word matters, because it is the formal way of saying no outside is required. So when someone asks where the center is, the best response is geometric rather than evasive. The center is not missing, and it is not hidden behind an observational curtain. The concept is misapplied to a space that expands uniformly. Expansion is not a motion away from a location. Expansion is a change in the metric that defines separation, and it is encoded in the scale factor that multiplies spatial distances. Asking for a center is like asking for the northernmost point on Earth that is not the North Pole. It is a request the geometry does not support. This does not mean every coordinate system looks the same, because coordinates are choices, not physical objects. You can choose coordinates that place you at the origin, and the math will cooperate without complaint. You can also choose coordinates that place another galaxy at the origin, and the same physical predictions will emerge. The physics stays invariant because the symmetry is built into the FRW description, and because general relativity does not privilege a particular coordinate grid. Coordinates can make patterns look different, but they cannot manufacture a real center where the symmetry forbids one. A useful way to phrase it is this: the universe has no preferred here, but it does have a preferred notion of cosmic time in the FRW model. Comoving observers, those who see the universe as isotropic, share a natural slicing of spacetime into spatial hypersurfaces labelled by that time. On those slices, the expansion is described by the scale factor, and the recession pattern becomes a property of the geometry rather than a swarm of trajectories. In practice, the cosmic microwave background provides a reference frame, because an observer at rest with respect to it sees no dipole anisotropy. That is not an absolute rest frame in Newton's sense, but it is a physically meaningful cosmic standard. Our own motion shows up as a dipole temperature pattern, a faint hot and cold gradient that tells us we are not perfectly comoving. The deeper question becomes shape, not location, and that question has a long intellectual ancestry. What is the geometry of the spatial slices at a given cosmic time? What does curvature mean when we are not picturing space as a sheet? Geometry answers with rules for triangles, angles, and parallel lines, and those rules can be tested, at least in principle, with light and with standard rulers. The history runs from Euclid's axioms to Gauss's intrinsic curvature and Riemann's generalization, long before Einstein turned those abstractions into gravity. Curvature is not primarily about bending into a higher dimension, even though that picture can be helpful for intuition. Curvature is about how distances and angles behave internally, without any reference to an outside. In flat Euclidean space, triangle angles sum to 180 degrees, and the ratio between circumference and radius is always 2p. In curved spaces, those relationships shift in systematic ways, and the shifts accumulate with scale. A small region can look almost flat, yet a large survey can reveal the slow drift of geometry away from Euclid's rules. Positive curvature is spherical geometry, and it has a distinctive feel once you live inside its rules. Draw a large triangle on a sphere using great circles, like lines of longitude and the equator. The angles add to more than 180 degrees, and the excess grows with the triangle's area. Lines that start parallel in the everyday sense can meet, because great circles eventually intersect. In a positively curved space, geodesics have a tendency to reconverge, as if the world gently wraps back toward itself. The visual is almost cinematic. A traveller walks due north from the equator, Another traveller begins a few kilometres east, and both keep their compasses fixed. At first they seem to remain separated, and the ocean between them looks constant. Yet the meridians converge, and the separation shrinks without either traveller ever turning. Near the pole, the two paths meet, not because the travellers chose to aim at each other, but because the geometry guided them together. In that moment, straight reveals its true meaning. It is not a line on a map, but the path that locally minimises distance. Zero curvature is the flat case, the geometry that matches the intuition of a rigid grid. Triangles at 180 degrees at all scales, at least in the ideal limit. Parallel lines remain parallel in the Euclidean sense, and the area of a circle grows as PR2. When we say space is flat, we mean these internal rules hold, not that space is a plane floating somewhere. Flatness is a statement about how rulers and angles behave when you build them into the space itself. In cosmology, nearly flat means any deviation is so small that even very large triangles would show only a tiny angular mismatch. Negative curvature is hyperbolic geometry, and it behaves like a space with extra room. Large triangles have angle sums less than 180 degrees, and the deficit grows with area. Parallel lines diverge in multiple ways, because there are many geodesics that never meet a given geodesic. If spherical geometry makes paths converge, hyperbolic geometry makes them peel away from each other. The visual is like a saddle surface, but the real meaning is internal. Circles have more circumference than Euclid would predict for the same radius. In such a space, volumes grow faster with distance, so how much room is out there changes in a measurable way. These are not abstract games played on chalkboards for their own sake. Curvature changes how volumes grow with radius, so the number of galaxies within a given distance depends on the geometry. It changes how a fixed physical scale projects to an angle on the sky, which is why the cosmic microwave background can constrain curvature. It changes how light paths and geodesics behave across large distances, subtly shaping the lensing of distant objects. Even the way time delays accumulate in gravitational lens systems can carry geometric information, because distance in cosmology is tied to the metric. Geometry, in other words, is not decoration. It is an observable ingredient in the bookkeeping of the universe. In FLW cosmology, curvature is a parameter in the spatial part of the metric, often written as k taking values that correspond to positive, zero or negative curvature. That parameter tells you the sign of the curvature, and it sets a curvature radius when combined with the scale factor. Yet it does not by itself tell you whether space is finite or infinite. That separation is unsettling at first, because everyday intuition expects curved to mean closed, and flat to mean endless. In relativity, that expectation becomes a question you must earn with mathematics. The sign of curvature is geometry, but finiteness can depend on topology, which is a different layer of structure. A positively curved space can be finite without an edge, and the clean analogy is two-dimensional beings living on a sphere. They can measure distances and angles on their surface, and they can map their world using only internal measurements. Their cartography works without any mention of an external room, because the room is not part of their physics. They never encounter a boundary, because there is no boundary to encounter. Their world is complete as a surface, even though it has a finite total area. If they built triangles large enough, the angle excess would quietly betray the curvature, like a signature hidden in the sum of their measurements. They could travel in a straight line, meaning along a geodesic, the closest analogue to no turning that their geometry allows. If they keep going, they eventually return to their starting point, approaching from the opposite direction. Their world has finite area, yet it has no edge. It is bounded in size, but unbounded in the sense of no boundary. That difference between finite and edgeless is one of the deepest repairs cosmology makes to ordinary language. It forces us to separate where it ends from how big it is, because those are not the same question. Now extend the analogy to three spatial dimensions, where the pictures become harder, but the logic stays intact. The three-dimensional analogue of a sphere is a three-sphere, a closed three-dimensional manifold with positive curvature. It is not a ball in ordinary space, and it is not the interior of a sphere. It is the higher dimensional generalization of a surface that closes on itself. You cannot point to its middle from within, because middle is an embedding idea, not an intrinsic one. If you tried to draw it, you would inevitably cheat by adding an extra dimension, and the drawing would smuggle in an outside that the model does not require. In that model, space is finite in volume, yet there is no edge to fall off. You can move in a straight geodesic direction and eventually return, although the distances involved could be unimaginably large. The universe can expand by increasing the scale factor while remaining closed, and the curvature radius grows as the scale factor grows. Nothing needs to surround it for the geometry to evolve. The expansion is a change in the internal metric, not a swelling into a surrounding emptiness. Even the word outward becomes a metaphor that must be handled carefully, because there is no exterior direction to point toward. This is where the phrase expanding into nothing becomes a category mistake, an error of grammar disguised as a physical demand. It assumes expansion requires an exterior, like gas filling a room. A closed universe expands by changing its internal distance scale, and the total volume can grow while still having no boundary. The expansion is not a frontier moving outward. It is the ruler itself changing. If you insist on an outside, you're asking for a different kind of model than the one the equations are describing. The flat case is even more deceptive, because it invites the strongest intuitive leap. Flat geometry does not guarantee infinite extent, and that is a subtle point with major consequences. Flatness is local and geometric, describing how small neighborhoods behave. Finiteness can be global and topological, describing how the entire space is connected. The universe can look like an endless grid in every direction, while still being globally wrapped in a way that only very long journeys could reveal. This is the distinction between geometry and topology, and it is one of the quiet revolutions of modern mathematical thinking. Geometry is about curvature and local distance relations, about what happens to triangles and circles when you zoom in. Topology is about global connectedness and identification of points, about whether paths can wrap around and return. Two spaces can share the same local geometry and differ globally, like two books with identical pages bound in different ways. The ink on each page is the same, yet the story of how pages connect can change everything. In cosmology, that difference becomes physical, because the global identifications determine what far away even means. A simple example begins in 2 dimensions because our minds can still picture it. A flat sheet is infinite if left unmodified, extending without limit in every direction. But if you identify opposite edges of a rectangle, gluing left to right and top to bottom, the sheet wraps into a torus. Locally it remains flat, yet globally it is finite and edgeless. The geometry does not announce the trick at small scales, because small triangles still add to 180 degrees. Only when you try to map the whole world you discover that going straight forever can bring you home. The torus image can be made vivid. A tiny ant walks straight across the surface, never noticing any seam, because the seam is not a physical wall. After a long walk, the ant returns to where it began, not because it turned around, but because the surface is connected that way. Every local measurement says flat, but the global journey reveals a hidden loop. The ant's world is finite, yet it never encounters an edge. The surprise is not in the ant's steps, but in the way space itself has been stitched. The 3-dimensional version is a 3 torus, and it is stranger only because we cannot embed it cleanly in our everyday imagination. Imagine a cube of space where opposite faces are identified, so exiting through one face means re-entering through the opposite face. Travel far enough in one direction, and you return from the other side. The geometry can be flat everywhere, while the topology makes the volume finite. In such a universe, straight paths can be globally circular, even though locally they never curve. The identification is not a barrier, and it is not a portal. It is simply how the space is defined. This possibility matters because near flatness is what observations suggest, and the evidence comes with a specific texture. The cosmic microwave background power spectrum constrains curvature tightly, because the angular size of the sound horizon at recombination acts like a standard ruler. That sound horizon is the maximum distance pressure waves could travel in the early plasma before atoms formed and photons decoupled. The first acoustic peak sits where a nearly flat geometry predicts, and the higher peaks reinforce the story. Yet the data constrain curvature, not topology, because topology hides in global identifications that may lie beyond our horizon. The CMB is a remarkable tool, but it is still a single spherical shell of information, and it cannot automatically reveal the full global wiring of space. Near flat means the radius of curvature is large compared to our observable patch, so our region looks Euclidean to high precision. It does not tell us whether space wraps around beyond our horizon, because the horizon limits what we can see. It does not tell us whether the global volume is infinite, because infinity is not an observable distance. It tells us that within the sphere of what light has had time to reach us, geometry behaves almost like a grid. That is a powerful statement, but it is not the final word. The universe could be globally simple, or globally stitched in a way that hides just beyond the reach of our most ancient photons. Topology, if non-trivial and small enough, could leave signatures that are almost poetic in their implication. Light could traverse the universe more than one way, arriving along different geodesics from the same region. The same physical structures could appear in multiple directions on the sky, like a hall of mirrors built from space-time itself. The cosmic microwave background could contain repeated patterns, not because the early universe repeated, but because the space carrying the pattern wraps around. The sky would not be larger, but it would be connected in a more intricate way. If that happened, the universe would be telling us that elsewhere can sometimes be here again, only approached from another direction. One proposed signature is matched circles in the CMB, a test that turns the sky into a geometric puzzle. If the last scattering surface intersects itself because of wraparound, circles of temperature fluctuations could match in pairs. The idea is conceptually clean, and it has an almost detective-like elegance. The same physical circle on the last scattering surface would be seen from two directions, so the hot and cold pattern along the circle would repeat. The search is difficult because noise, foreground emission, and cosmic variance complicate the pattern, and because real data are never as pristine as the theory sketch. Even subtle effects like gravitational lensing can blur the primordial pattern, adding another layer of complication to an already delicate test. So far, no convincing matched circle signal has been found, and that absence is informative but not final. No detection does not prove infinite space, because a finite topology could simply be too large to reveal itself. It sets lower bounds on the size of any wraparound scale, pushing the fundamental domain beyond the observable universe. If the universe is a 3 torus, it may be a torus so large that our horizon is a small patch on one face. The topology could be there, and we could still be too locally confined to notice. The silence of the data is not a verdict, but it is a constraint. This is the observational humility built into cosmology, and it is not a rhetorical flourish. We see a finite volume because light has travelled a finite time, and because the universe has a finite age in our models. The observable universe is bounded by a horizon, not by a wall, and horizons are about information rather than material edges. The whole universe could be much larger than what we see, or it could be infinite, and the data may never fully decide. The horizon is not a border in space, but a limit on what events can influence us. Even if space extends without end, our causal access to it is filtered through time. Curvature constraints also face limits that are easy to underestimate. The CMB gives a snapshot of early times, but it is filtered through late-time physics, including the integrated effects of expansion and gravitational potentials. Parameter degeneracies allow small curvature to trade off with assumptions about dark energy behavior and the expansion history. Improved data tighten the box, but they cannot remove the horizon, and they cannot turn a finite observational cone into a view of the whole. Even the best maps of the sky are still maps drawn from one location. The universe does not hand us its global blueprint, and it never promised to. Historically, this tension between what can be measured and what can be inferred has shaped cosmology from the beginning. Einstein introduced curvature into the structure of space-time, and early debates over whether the universe was static or dynamic were debates about geometry as much as about matter. His original static model required a cosmological constant as a balancing term, a mathematical counterweight to gravity's pull. Friedman and Lemaitre showed that expanding solutions were natural in general relativity, long before the observational case was settled. Their work reframed the universe as something that could evolve, not merely sit. The idea that the cosmos could have a history was not just a discovery, but a change in what physics allowed itself to imagine. Hubble's redshifts then gave the expansion a foothold in data, and the language of expansion began to compete with the older language of motion. Even then, interpretation was not immediate, because redshift can also arise from motion in ordinary space. The conceptual shift was to treat the redshift as cosmological, tied to the metric and the scale factor. That shift turned the sky into evidence for geometry. Over time, the evidence grew from a trend in galaxy spectra into a precision framework, with supernovae, baryon acoustic oscillations, and the CMB all cross-checking the same expansion story. Even the term Big Bang entered as a critique, a phrase meant to mock the idea of a cosmic beginning, yet the name stuck perhaps because it captures the drama even while misleading the imagination. The real lesson of the FLAW model is quieter, and in some ways more unsettling. The early universe is not a point in space. It is a condition of the entire spatial slice at early cosmic time. The bang is not a place you could travel to, because every place was once in that state. So the chapter's tension sharpens, because the idea of no edge removes one question and exposes another. If there is no edge, the universe is not expanding into an outside nothing. Expansion is internal, defined by the metric and the scale factor, yet the absence of an outside does not remove the deeper discomfort, because the mind immediately asks a different question. If the universe does not need an exterior, then what exactly does it need in order to begin? If there is no boundary, what happened at the beginning? If space is not inside anything, what does it mean for space to start? If time is part of the geometry, what does before mean, and what would it even refer to? These questions feel philosophical, but they are also technical, because general relativity ties time to the structure of space-time itself. In relativity, time is not a universal background ticking independently of the universe. It is part of the dynamical object we are trying to describe. When we ask about before, we may be asking for a coordinate that the model does not contain. In standard cosmology, the Big Bang is not a place in space, and it is not a location you could point to on a map. It is a limit in time where the scale factor shrinks and densities rise, and where the universe becomes hotter and more compressed. Every co-moving location shares that early hot, dense state, and the same cosmic time coordinate labels it everywhere. Running the equations backward does not point to a spatial center, because there is no special co-moving point. It points to a global condition, like rewinding a film that was shot everywhere at once. The remarkable implication is that the beginning is not somewhere else, it is everywhere, but earlier. But running backward does point to a breakdown, and the breakdown has a precise mathematical character. Classical general relativity predicts singular behavior in simple models, where curvature invariants grow without bound, and geodesics become incomplete. In plain language, the theory stops giving sensible answers about what happens earlier than a certain limit. That is not necessarily a real physical point. It can be a sign that our model has reached its domain limit, like a map that ends at the edge of its ink. The equations are telling us, in their own language, that something is missing from the description. This is where the word singularity can mislead, because it sounds like an object. In the equations, it is often a signal that some quantity diverges, and that the classical description is missing new physics. The singularity theorems show that under broad conditions, incompleteness is hard to avoid, which makes the question unavoidable. Yet they do not tell us what replaces the breakdown, because the replacement may require quantum gravity. The honest story is not that we have reached a final answer, but that we have reached the boundary of a theory. The boundary is conceptual, not spatial, and it sits where our trusted tools stop working. The unsettling implication of geometry without an outside is that the universe does not need an exterior to expand, yet the geometry itself has a history. The metric evolves, the scale factor changes, and the energy content influences that evolution through Einstein's equations. Matter and radiation do not merely move within space-time, they help determine how space-time stretches and how quickly it does so. In that sense, the universe is not a stage with actors on it. It is a coupled system where the script and the set are written together. The question becomes what sets the initial conditions for geometry and matter, and why those conditions are the ones we see. Why is the universe so nearly homogeneous on large scales, when gravity tends to amplify differences? Why is curvature so close to zero, at least within our horizon? Why do the fluctuations in the CMB have the particular spectrum we measure, with its delicate pattern of peaks and troughs? Even if where is the centre dissolves, why this beginning remains? And behind that remains a quieter question. Are these features inevitable outcomes, or contingent facts about our cosmic history? Some proposals replace the singular beginning with a bounce, where contraction precedes expansion and the scale factor never reaches zero. Some propose quantum creation scenarios where classical time emerges from a more fundamental description, and the word before loses its ordinary meaning. Some propose inflation as an early dynamical phase that smooths curvature, and stretches any small-scale topology beyond view, making the universe appear flatter and more uniform than it otherwise would. Inflation also changes the way we think about initial conditions, because it can erase memory of earlier irregularities. None of these answers is settled in this chapter, and the uncertainty is part of the honest landscape. The mystery is not just what happened, but what kinds of evidence could ever distinguish one beginning from another. What matters here is the shift in what we are allowed to ask, and what questions remain physically meaningful. Where is the center is the wrong question in an FLRW universe, because it assumes a geometry the model does not contain. What is the global shape is a meaningful question, but it may be unanswerable beyond bounds set by horizons and cosmic variance. What happened at the beginning is meaningful, but it may require physics beyond classical spacetime, because the classical description predicts its own failure. The mystery is not an invitation to abandon rigor, it is an invitation to sharpen what rigor can reasonably demand. If the universe refuses to provide an outside, then our questions must become internal, operational, and testable. So the paradox evolves, and it becomes more precise rather than more mystical. Expanding into nothing is a grammar error when space has no edge, because it treats expansion like invasion of an external region. The real mystery is why the geometry exists, and why it evolves in the way it does, with a scale factor that changes according to the universe's contents. The universe does not expand into an outside. The universe expands by changing the inside. Transition. If shape can remove the need for an exterior, origin becomes the next pressure point. Transition. We move from the geometry of space to the origin of space-time, where the Big Bang marks a limit of our models. We now carry forward two tools, and they are more than metaphors. Geometry tells us what local curvature means and how it affects observations, from the angular scale of CMB features to the way volumes grow with distance. Topology tells us that even flat space can wrap and be finite, hiding its global structure beyond our horizon. Together they dissolve the demand for an outside while sharpening the question of beginnings. They also remind us that the universe can be simple in its rules and still profound in its implications. If the cosmos is edgeless, then our most basic intuitions about where must yield to what measurement and mathematics can actually define. The next chapter follows that sharpened question into dynamics, where the narrative turns from maps to motion. If the scale factor changes, what governs its evolution, and how do we write that change as an equation rather than an image? If energy content shapes curvature, how does it set expansion history across radiation, matter, and dark energy-dominated eras? We leave the map of space and turn toward the equations that drive spacetime itself. We have removed the edge, and we have removed the center, yet the mind still reaches for a beginning. Expansion does not require an outside, but it seems to demand a first moment. Some clean starting gun that makes the story feel intelligible. Chapter by chapter, the paradox is narrowed into a sharper question about time itself, because time is not merely a backdrop in modern cosmology. If space-time is the thing evolving, what does before even point to when the coordinate grid is part of the phenomenon? On screen, imagine a grid drawn on a dark plane, then slowly stretching, the squares widening as if the paper itself were breathing. The temptation is to picture an explosion into surrounding emptiness, yet the mathematics insists on something stranger, space creating more of itself. That difference sounds philosophical, but it is actually operational, because it changes what our equations are allowed to mean. When we ask for a beginning, we are asking whether the equations can be extended, and whether time remains a usable parameter. The hot Big Bang model is not a creation myth, it is a successful extrapolation built from tested physics. It starts with a hot dense plasma and follows cooling as the scale factor grows, with radiation dominating early because its energy dilutes faster than matter. Run the equations backward, and temperature rises, densities climb, and reaction rates explode, because particles collide more often in a tighter, hotter universe. The cosmic microwave background and light element abundances anchor this story with hard numbers, not just qualitative sketches. The early universe was real physics, not a metaphor, and it left measurable relics that still fill the sky. Visually, the narrative begins in a fog of ionized gas, electrons and nuclei scattering light so efficiently that the universe is opaque. As expansion proceeds, that fog thins, and the cosmos transitions from a glowing plasma to a transparent, cooling sea of radiation. The key point is not that we see the beginning, but that we see a boundary where the universe first became transparent to photons. That boundary, the surface of last scattering, is a physical event tied to atomic physics and the recombination of electrons with protons. The success of the hot Big Bang was not immediate, and it arrived through a sequence of predictions that could have failed. In the 1940s, early nuclear calculations suggested that a hot beginning would forge light elements, and those ratios could be checked later. Decades afterward, the discovery of the cosmic microwave background provided the missing thermal afterglow, a near-perfect blackbody spectrum at about 2.7 Kelvin. That spectrum is a fingerprint of equilibrium, and it is remarkably difficult to fake with astrophysical sources that turn on later. When we say extrapolation, we mean a chain of inferences that survived contact with data. But extrapolation has a limit, and the limit is not just practical, it is conceptual as well as mathematical. In classical general relativity, the scale factor can shrink towards zero in finite proper time, which means a time-like observer reaches the boundary in a finite lifetime. Curvature invariants blow up, geodesics become incomplete, and the model stops being predictive because the equations no longer yield finite, stable answers. The singularity is not necessarily a place or an object. It is a signpost of missing theory, an alarm bell, not a destination. It tells us our classical description cannot be trusted arbitrarily close to the putative beginning, even if the equations still allow us to write symbols. On screen, the smooth grid of space-time begins to warp, then buckle, then fragment into a region where the lines lose meaning. The imagery is not literal, but it captures the point that geometry itself becomes ill-defined when curvature grows without bound. Classical relativity treats space-time as a differentiable manifold, meaning you can zoom in and still define slopes and distances. A singularity is where that assumption collapses, and with it collapses the ordinary idea that time is a continuous parameter you can extend. The breakdown is not a confession of failure. It is a map boundary marked, "Here be dragons," inviting a deeper framework. This is where language starts smuggling in assumptions that physics may not share, because everyday words carry hidden geometry. Nothing in everyday speech means absence, emptiness, and a blank stage waiting to be filled with actors and props. In cosmology, the stage is not separate, so blank stage is already a loaded phrase that presumes space and time exist without content. If time is part of the dynamical system, before time may be like north of north, grammatical yet physically undefined. The question is not only what happened first, but what counts as a meaningful earlier when the clock itself is part of the model. A subtle shift happens here, and it matters for the rest of the chapter. We are not merely hunting for an earlier event, as if the universe were a film reel with missing frames at the start. We are asking whether the concept of earlier survives the regimes where quantum effects and extreme curvature dominate. If the equations that define time break down, then before may be a request for translation rather than a request for a date. That is why the beginning question is both irresistible and treacherous. Transition. The Big Bang describes an early state everywhere, yet it points to a breakdown. The breakdown is not subtle, because the early universe also presents puzzles inside the model, even before we reach the singular limit. Two of them are famous because they are visible in the sky with almost embarrassing clarity, written across a map of microwaves. The first is the horizon problem, which begins with the smoothness of the CMB, a uniform glow that varies only slightly across the celestial sphere. Regions separated by more than a few degrees on the last scattering surface were causally disconnected, meaning light signals could not have crossed between them in time. In standard expansion without new ingredients, they could not have exchanged signals or equilibrated, so their temperatures should not match so closely. Yet their temperatures match to 1 part in 100,000 after subtracting our motion, a precision that feels like coordination without communication. The universe looks like it coordinated itself across distances it could not have communicated across, and that is the puzzle in plain language. Visually, the CMB appears as a softly mottled sphere, like a faintly speckled eggshell surrounding us in every direction. Then the camera pulls back, showing 2 distant patches on that sphere, far apart, each with nearly the same colour-coded temperature. A light cone diagram overlays the image, and the cones fail to overlap, leaving a gap where causal contact would have needed to occur. The discomfort is not aesthetic, it is dynamical, because thermal equilibrium is usually achieved by interactions that transmit energy and information. Without contact, uniformity looks like an unexplained initial condition. The second is the flatness problem, which begins as a bookkeeping issue in the Friedman equations, then grows into a statement about stability. Spatial curvature evolves differently from matter and radiation as the universe expands, because curvature terms scale with the inverse square of the scale factor. If curvature were not extremely tiny early on, it would quickly dominate and make space obviously curved, either rapidly recollapsing or expanding too fast for structure. Instead, observations indicate near-flat geometry within our horizon, with curvature consistent with 0 to impressive precision. That near-flatness looks like a fine-tuned initial condition when we run the clock backward, because any deviation grows with time in the decelerating eras. The early universe seems balanced on a knife edge, and the model does not explain why it started so close to that special value. To make the visual concrete, imagine drawing a triangle on cosmic scales and measuring whether its angles sum to 180 degrees. In a positively curved space, the sum is larger, and in a negatively curved space, it is smaller, yet our best measurements keep landing near the Euclidean answer. The flatness problem is the observation that near Euclidean is not a generic outcome in a decelerating universe unless it begins extremely close to flat. It is like balancing a pencil on its tip, except the balancing must persist across enormous changes in density and temperature. The question becomes, what mechanism could make flatness stable rather than accidental? A third tension is quieter but equally telling, because it concerns unwanted leftovers from high-energy particle physics. Grand unified ideas suggest phase transitions that could produce heavy relics like magnetic monopoles, topological defects that would be extraordinarily hard to eliminate later. The hot Big Bang does not obviously forbid them, yet the universe does not appear to contain them, despite careful searches in cosmic rays and materials. The early universe seems to have avoided certain outcomes that naive high-energy reasoning expects, which hints that the early expansion history may not be as simple as hot and then cooler. In a sense, the sky is not only telling us what is present, but also what is conspicuously absent. These problems are not proof the Big Bang is wrong. They are proof it is incomplete, because the later successes remain intact. They motivate a modification to the earliest expansion history, not a rejection of nucleosynthesis, recombination, or the broad thermal narrative. The proposed modification is inflation, a brief epoch of accelerated expansion before the hot Big Bang, inserted not as decoration but as a dynamical phase. Inflation is not more expansion. It is a different regime where the scale factor grows quasi-exponentially, driven by an unusual equation of state. In that regime, the comoving Hubble radius shrinks, and causal structure changes in a crucial way that reverses the usual intuition. Historically, inflation emerged in the early 1980s as a response to these fine-tuning puzzles, and it quickly developed into a predictive framework. The original versions were revised, improved and multiplied, because the mechanism depends on particle physics that we do not yet know in detail. Yet the core idea remained stable. A period of accelerated expansion can transform initial conditions into robust outcomes. Acceleration is the key, because in general relativity the sign of the pressure matters, and negative pressure can make expansion speed up. That is a counterintuitive statement, but it is encoded directly in the Friedman acceleration equation. Inflation is often described as the universe doubling again and again in a tiny fraction of a second, as if the cosmos were a rapidly inflating balloon. That description is crude, but it captures the key idea of rapid stretching of physical distances, where scales that were microscopic become astronomical. The driver is an energy component with negative pressure, behaving like an almost constant energy density even as the universe expands. In many models, this comes from a scalar field, with potential energy dominating over kinetic energy, so the field acts like a vacuum-like substance. The field slowly rolls, the energy density stays nearly constant, and the space-time expands at an accelerating rate, smoothing out irregularities as it goes. This is not an external push. It is the metric responding to a particular stress-energy configuration, the way curvature responds to energy in Einstein's equations. Visually, the inflationary phase is not a fireball, but a quiet stretching, like a fabric pulled taut so rapidly that wrinkles vanish. Any initial lumps in energy density are diluted, and any initial curvature is flattened. Not by force, but by the geometry's own evolution. The camera might show a tiny patch of space with quantum jitter, then a sudden expansion that turns that patch into a vast region. The remarkable claim is that the large-scale uniformity we see could be the stretched memory of a small, once-connected domain. Inflation turns the horizon problem into a story about what used to be inside the horizon. Inflation addresses the horizon problem by changing what used to be out of contact, and it does so through causal structure rather than mere speed. Before inflation ends, the region that becomes our observable universe can be small enough to equilibrate, because the co-moving horizon behaves differently during acceleration. Then inflation stretches that once-connected patch to scales far larger than the later causal horizon. So regions that look disconnected today were once neighbours. Uniformity becomes a memory of an earlier time when the patch was in causal contact, like a shared temperature imprinted before the stretching. The CMB's smooth temperature becomes less mysterious, though not magically guaranteed in every model, because reheating and field dynamics still matter. Inflation addresses the flatness problem by diluting curvature the way stretching dilutes any initial bend, and the mathematics is clean. As the scale factor grows rapidly, any initial spatial curvature is driven toward near zero, because the curvature term becomes negligible compared to the nearly constant energy density. After enough e-folds, space appears flat within any finite observational region, even if the global topology is more complicated than our horizon can reveal. Flatness becomes an attractor-like outcome, not a precarious initial setting that must be tuned to absurd precision. Inflation does not prove the universe is globally flat, but it explains why our patch looks that way with such stubborn consistency. Inflation also helps with relic problems by diluting unwanted heavy particles to negligible abundance, essentially by expanding the volume faster than relics can remain dense. If monopoles formed before inflation, their number density would be stretched away to near nothing, leaving the universe effectively cleansed of those heavy remnants. The absence of certain relics becomes less surprising, though it depends on when inflation occurs and how reheating repopulates particles afterward. The mechanism is simple in spirit: dilution through expansion, but the details depend on particle physics we still cannot test directly at those energies. Inflation, in that sense, is both elegant and incomplete, because it leans on unknown microphysics. Yet inflation is not only a patch for problems, it makes a risky claim about origins of structure, and this is where the story becomes almost unsettling. It says the large-scale patterns in galaxies began as microscopic quantum fluctuations, the unavoidable jitter of fields even in their lowest energy states. Quantum noise in fields becomes classical-looking density perturbations after being stretched beyond the horizon because causal contact is lost and phases effectively freeze. Modes exit the horizon during inflation, their amplitudes freeze, and later they re-enter to seed growth when the universe is older and slower. This is a bridge between quantum theory and cosmic structure, and it is one of inflation's boldest moves because it claims the universe's largest patterns began as the smallest uncertainties. On screen, the visualization can start with a calm, nearly featureless field, then show tiny ripples appearing like faint static. Those ripples are not added by hand, they are demanded by quantum mechanics, because fields cannot have exactly zero fluctuations in all modes. Then the camera pulls back as inflation stretches the ripples, turning subatomic variations into waves spanning light years, then millions of light years. Later, gravity amplifies those slight overdensities, drawing matter into filaments and nodes until the cosmic web emerges. The astonishing idea is that the universe's scaffolding is in part fossilized quantum randomness. The evidence for this bridge is indirect but detailed, and it lives in the CMB anisotropies, the tiny temperature differences across the sky. The temperature map is not random speckle. It has a statistical structure that can be measured, compared, and compressed into a few key parameters. We compress that structure into a power spectrum, describing fluctuation amplitude versus angular scale, and those peaks and troughs carry physical meaning. Inflation generically predicts nearly scale-invariant, adiabatic Gaussian primordial perturbations, which is a technical way of saying similar power on many scales with simple statistics. Measurements largely match that pattern, with a slight tilt that indicates more power on larger scales, consistent with a slowly changing inflationary expansion rate. The acoustic peaks then process those initial conditions through plasma physics at recombination. where sound waves in the photon baryon fluid leave standing wave signatures. The result is a spectrum whose detailed shape links early universe dynamics to late universe observations, tying quantum beginnings to microwave measurements. A useful visual here is a slow morph from the mottled CMB sphere into a graph, where the bumps in the sky become peaks in a curve. Each peak corresponds to a harmonic of oscillation in the early plasma, a kind of cosmic instrument whose resonances we can still hear in temperature and polarization. Baryons add inertia, photons provide pressure, and gravity provides the restoring pull, so the system behaves like a driven oscillator on enormous scales. The spacing and heights of the peaks encode the matter density, baryon fraction, and geometry, making the CMB a precision tool rather than a mere picture. Inflation sets the initial phases, and the plasma physics conducts the later symphony. Inflation also predicts a specific kind of phase coherence in the perturbations, and this is one of its more subtle successes. The peaks line up in a way consistent with fluctuations being laid down as a single set of initial phases, like synchronized starting conditions for many oscillators. Alternative mechanisms can struggle to reproduce that coherence without reintroducing fine-tuning, because incoherent sources tend to smear peaks into a blur. This is not a final verdict, but it is part of why inflation became the leading framework, even among scientists who remain cautious about its deeper implications. The universe, in the CMB, appears to remember a clean set of initial conditions. There is another prediction that remains a frontier, and it is tied to gravity itself, where observation becomes especially demanding. Quantum fluctuations of the metric should produce primordial gravitational waves, ripples in space-time that would stretch and squeeze distances as they pass. Those waves could imprint B-mode polarization patterns in the CMB, a faint swirling signature distinct from the gradient-like E-modes. The search is difficult because foreground dust and lensing can mimic or obscure the signal, and separating them requires careful multi-frequency maps. Non-detection sets upper limits on the inflationary energy scale and rules out some models, especially those predicting large tensor-to-scalar ratios. A detection would be a major clue, but it would still not uniquely identify the inflation mechanism, because different potentials can produce similar gravitational wave amplitudes. Visually, polarization can be shown as tiny line segments on the sky, then decomposed into patterns, one curl-free, one curl-like. The narrator can linger on the faintness. This is not a bright beacon, it is a whisper under layers of astrophysical noise. Even so, the stakes are high, because a primordial gravitational wave signal would connect quantum fluctuations directly to spacetime itself. It would also hint at the energy scale of inflation, a regime far beyond any particle accelerator. The early universe becomes the laboratory, but the detectors must be exquisitely patient. Inflation therefore shifts the beginning question rather than closing it, and this is where the chapter's mood deepens. It can make the early universe smoother, flatter, and structured in a predictable statistical way, which is an extraordinary explanatory gain. But it also raises the issue of what started inflation and what conditions made it likely, because a mechanism can still require a setup. If inflation needs special initial conditions, we have moved the fine-tuning problem, not erased it, relocating the mystery to an earlier boundary. If inflation is generic, we must explain why the laws allow such a phase at all, and why the field lands in the right region of its potential. This is where the word nothing returns, because inflation is often sold as creation from nothing, a phrase that sounds decisive in a headline. That slogan is not physics. It is a compression that hides the machinery, and the machinery is precisely what matters. Inflation requires a space-time arena in which a field has dynamics and energy density, even if that arena is small and short-lived. It requires quantum fields that fluctuate, and a gravitational theory that responds to energy and pressure, because without those rules, there is no inflationary engine. Even in the simplest story, nothing has already been replaced by a structured physical framework, complete with equations, symmetries, and assumptions. Modern physics describes reality in terms of fields, not just particles as tiny billiard balls moving through emptiness. The electromagnetic field exists even where there are no photons in the classical sense, because the field is the underlying entity, and photons are excitations. The electron field exists even in regions without electrons as excitations, and the same is true for quark fields, neutrino fields, and more. The vacuum is the lowest energy state of these fields, not the absence of the fields themselves, and that distinction is central to the nothing debate. A field can have a non-zero expectation value, and it can store energy in its configuration, shaping particle masses and interactions. Space that looks empty can still have properties that affect forces, masses, and expansion, which is why emptiness in physics is rarely featureless. Visually, emptiness becomes a layered image, a dark expanse, then faint grids and wave patterns, then subtle fluctuations like shimmering heat haze. The narrator can emphasize that the vacuum is not a void in the everyday sense, because it is defined by a state of a system, not by the absence of a system. In quantum theory, you do not remove the field when you remove the particles, you simply place the field in its ground state. That ground state still carries correlations, and in curved space-time it can even be observer-dependent, complicating what empty means. The universe forces us to be precise because our intuitions were trained on rooms, air, and silence. Quantum field theory adds a second layer of discomfort to the naive idea of emptiness, because even the ground state seethes with irreducible uncertainty. Even in the vacuum state, fields have zero-point fluctuations constrained by uncertainty relations, meaning certain quantities cannot be simultaneously sharp. Virtual excitations are not particles popping in and out like cartoons, but the vacuum is not inert, and its fluctuations can influence measurable forces. Correlations exist, fluctuations exist, and energy scales matter, even when no classical matter is present, because the vacuum responds to boundaries and geometry. The Casimir effect is one concrete sign that vacuum structure can have measurable consequences, producing an attractive force between closely spaced conducting plates. In cosmology, vacuum energy behaves like a fluid with negative pressure in the Friedmann equations, and that is precisely the kind of ingredient that can drive accelerated expansion. The pressure point, literally, is worth slowing down for because negative pressure sounds like a trick of words. In general relativity, pressure contributes to gravity, and a sufficiently negative pressure leads to repulsive gravitational effects on large scales. A vacuum-like component has pressure approximately equal to minus its energy density, so as the universe expands, it does not dilute the way matter does. That persistence is what makes it powerful, because it can dominate the energy budget and force the expansion rate to accelerate. Inflation, in many models, is simply the universe briefly dominated by such a component. This is why the ambiguity of nothing is not pedantic. It changes the question's meaning, and it changes what counts as an answer. We can mean empty space in the everyday sense, with no atoms and no radiation, like a perfect laboratory vacuum. We can mean a quantum vacuum state, with fields present but in their lowest energy configuration, still capable of fluctuations and stress energy. We can mean the absence of classical spacetime itself, with no geometry to define distance or time, which is a far more radical claim. Each meaning implies a different set of laws and a different set of things that can fluctuate, because fluctuations require a system. Each meaning changes what it would even mean to expand into something, because expansion is a statement about geometry, not about motion through a container. If nothing means empty space with quantum fields, then there is already a metric and a vacuum state, and the universe is already something. Expansion is then a change in geometry, and the vacuum is a physical medium with stress energy, even if that stress energy is subtle. The universe does not expand into that vacuum, because that vacuum is part of the universe's description, not an external arena. The outside is not a location. It is a mistaken picture of a container, like imagining the surface of a sphere expanding into the room around it. The correct picture is intrinsic. Distances between co-moving points grow, even though there is no edge moving outward. If nothing means the lowest energy vacuum, we still face a crucial question, because lowest can be plural in field theory. Is the vacuum unique, or are there multiple metastubble vacua with different energy densities, separated by barriers in a potential landscape? In field theory, potentials can have several minima, and the universe can occupy a false vacuum temporarily, like a ball resting in a shallow valley. A false vacuum can drive inflation, then decay to a lower energy state, reheating the universe by converting vacuum energy into particles and radiation. In that story, the hot Big Bang is not the start, it is the aftermath of vacuum decay, a thermalization event that fills space with a hot plasma. The beginning becomes a phase transition, not an absolute origin, and the earliest meaningful moment becomes the onset of a particular vacuum state. Visually, a potential curve appears, with a ball perched in a higher valley, then tunneling or rolling into a deeper valley. When it drops, the energy difference becomes heat, and the screen floods with particles like sparks filling a dark chamber. Reheating is not a metaphor, it is the physical process that repopulates the universe with the ingredients of the hot Big Bang. The temperature after reheating sets the stage for later processes, including baryogenesis scenarios and the eventual formation of light elements. Inflation, in this view, is a prelude whose ending is the first hot luminous act. If nothing means no classical spacetime, then we are outside the domain of standard cosmology, and our usual tools lose their footing. General relativity assumes a differentiable manifold and a metric that defines intervals, so it presupposes the very thing we're trying to remove. Quantum field theory assumes a background structure to define modes and commutators, which again presumes a notion of time and space to begin with. A true absence of spacetime would require a deeper framework where geometry emerges, perhaps from more primitive degrees of freedom. In such a framework, time may be emergent, and before may not be well defined, because the ordering itself could be a derived concept. The paradox of expanding into nothing dissolves, but it dissolves by removing the stage entirely, leaving us with a different mystery about emergence. Inflation sits uncomfortably across these meanings, because it uses fields and geometry to explain origins while inviting slogans that imply literal absence. It offers a mechanism for smoothing and seeding structure, but it does not begin from literal absence, and it does not abolish the need for laws. Even quantum creation scenarios typically assume laws, amplitudes, and a configuration space, which is already a kind of structure. The mystery shifts from what did it expand into to why are there laws and fields at all, and that shift is not a dodge. It is a recognition that physics answers questions within frameworks, and frameworks are not nothing. There is a further twist that inflation introduces, and it is where caution becomes necessary because the mechanism may not be globally tidy. In many models, inflation is not a one-time event that ends everywhere on a single global clock, because quantum fluctuations can affect the field's local evolution. Quantum fluctuations can keep some regions inflating, while other regions exit and reheat, producing a patchwork where different domains have different histories. This is eternal inflation, where inflation continues in pockets and ends in bubble universes, each bubble a region where the field fell into a lower energy state. Each bubble can have its own local hot Big Bang, its own expansion history and perhaps different low-energy physics, if the vacuum structure allows variation. The multiverse is not a fantasy add-on, it is a possible consequence of how inflation works in some potentials, though it remains a controversial implication. On screen, the image becomes cellular, inflating space as a rapidly swelling background, punctuated by bubbles that nucleate and expand within it. Inside each bubble, the familiar hot universe begins, while outside, the inflating region keeps stretching, making new room for more bubbles. The narrator can pause on the scale, because the process can generate enormous volumes, dwarfing any single region like ours. The unsettling part is not multiplicity itself, but the way it complicates explanation, because typical becomes hard to define. When everything happens somewhere, prediction risks becoming selection, but the multiverse is also where testability becomes strained, and cosmology becomes careful with its claims. If other bubbles are causally disconnected, direct observation may be impossible in principle, because no signal can cross the inflating regions between them. Some proposals look for bubble collision signatures in the CMB, such as circular anomalies or specific non-Gaussian patterns, but no robust evidence has emerged. Measures over infinite volumes introduce ambiguities, and probabilities become hard to define, because counting outcomes depends on how you regulate infinity. The framework can drift from explanation to landscape, where almost anything happens somewhere, and that is why the idea is handled with restraint. Inflation is presented with both respect and caution in serious cosmology, because explanatory power must remain tethered to observational discipline. Even without eternal inflation, the beginning remains slippery, because inflation can act like a veil as well as a solution. Inflation can push the initial conditions back to an earlier pre-inflationary era, where we again face unknown physics and unknown boundary conditions. It can also make our observable patch insensitive to what came before, erasing information by stretching away pre-existing gradients and relics. That is a triumph for explaining smoothness, but it is a problem for reconstructing ultimate origins, because erased information cannot be recovered. The better inflation works as a cosmic eraser, the less it tells us about what preceded it, and the less it can answer the deepest why questions. This tension echoes the earlier theme about horizons, now applied to time rather than space, and the analogy is more than poetic. A horizon limits what we can see across distance, because light has finite travel time, and the universe has a finite age. Inflation creates an effective horizon in the past, because it can hide pre-inflationary structure behind an exponential stretching that makes earlier regions unobservable. Our data may be consistent with many prehistories that inflation has washed away, leaving only a narrow set of observable consequences. The universe may be telling us that some questions are not forbidden, but underdetermined, meaning multiple stories fit the same evidence. We can now reconnect to the documentary's central question with a sharper vocabulary, because precision is what dissolves false paradoxes. The universe does not expand into an external nothing, because expansion is intrinsic geometry, a statement about how distances change within space-time. Inflation does not require an outside either, because it is a dynamical regime of the same metric, driven by stress energy rather than by motion through emptiness. What changes is not where the universe goes, but how its scale factor evolves with its contents and how that evolution reshapes causal contact. The container picture fails again, now at the earliest times where intuition is most desperate and where language is most likely to mislead. The phrase, before the beginning, is therefore not just poetic, it is a technical warning about domains of validity. If time is part of space-time, then time itself may have a domain of validity, just as temperature loses meaning outside thermodynamic equilibrium. If the classical model breaks at a singularity, then t equals 0 is not a physical moment, it is a coordinate label attached to a boundary of the model. If quantum gravity replaces the beginning with something else, the word before may need translation, because the underlying variables may not include time in the usual way. Inflation may be part of that translation, but it is not the final dictionary, and it does not guarantee that the beginning is a moment rather than a boundary. We also carry forward the Hubble tension, because it hints that our standard story may be incomplete in ways that touch the early universe. If early universe physics differs slightly from the simplest model, it can shift CMB inferred parameters, changing how we infer today's expansion rate from ancient light. Extra radiation-like components, early dark energy, or modified recombination could change the sound horizon, which is the standard ruler imprinted in the CMB and baryon acoustic oscillations. Those changes could reconcile A0 values, but they must also preserve the CMB peak structure, which is measured with extraordinary precision. Inflation sets initial conditions, but late-time inference depends on the full chain from recombination to today, including how matter clusters and how light propagates. The tension is a reminder that the early universe is not only ancient, it is still active in our equations, because today's numbers are extracted from yesterday's physics. Visually, the chapter can briefly return to the ladder of inference, CMB peaks, then a sound horizon ruler, then a plot of H0 values that do not quite meet. The narrator can stress that this is not a minor bookkeeping error, because the disagreement persists across methods that use different astrophysical assumptions. If the tension survives future data, it may indicate missing ingredients in the early universe, which would ripple back into our understanding of inflationary initial conditions. If it fades, it will still have served as a stress test, showing how tightly our cosmic narrative is constrained. Either way, it demonstrates that cosmology is not only about the past, but about consistency across many eras. And we carry forward the late-time acceleration problem, now with a new conceptual mirror that makes the mystery feel symmetrical. Inflation is early accelerated expansion, driven by something like vacuum energy, a brief domination by a nearly constant energy density. Dark energy is late accelerated expansion that also behaves like vacuum energy in the simplest model, though its microphysical origin remains unknown. The universe may have accelerated twice, for reasons that look mathematically similar but physically mysterious, like two echoes of the same unresolved principle. If vacuum energy can drive expansion, why is its value what it is today, and why did it become dynamically important only recently? If fields can store enormous energy scales, why is the present acceleration so small, and why does it not gravitate in the naive way quantum field theory suggests? The cosmological constant problem sits behind this, unresolved and deeply unsettling, because it exposes a mismatch between theory and observation. So the meaning of nothing becomes the hinge of the chapter, because it determines whether our questions are coherent or confused. Empty space is not empty, because fields and fluctuations are part of the description, and they can have observable effects even when matter is absent. A vacuum state is not absence, because it has structure and can gravitate, and its energy can influence the expansion history. No space-time at all is not a vacuum. It is a different category where our usual equations fail, and where time may not be fundamental. When we ask how the universe expands into nothing, we often slide between these meanings without noticing, and the slide creates a paradox that feels deeper than it is. The paradox survives in language, but it weakens under careful definitions, because many versions of nothing are actually something in disguise. Inflation offers a coherent early universe narrative, but it also raises the stakes, because coherence is not the same as closure. It can explain why the universe looks smooth, flat and seeded with the right kind of randomness, turning fine-tuning puzzles into dynamical outcomes. It can connect quantum fluctuations to the large-scale structure we map in galaxies, and the CMB, linking microphysics to the cosmic web. It can make the Big Bang a reheating event rather than an absolute origin, shifting the beginning from a singular point to a transition between phases. Yet it can also imply eternal reproduction of universes, and it can hide the ultimate beginning behind a veil, making the deepest boundary harder to access. The more we learn about early expansion, the more the word beginning starts to look negotiable, like a term that depends on the resolution of our theory. Transition. Inflation may explain the early behavior of expansion, but it threatens to dissolve the very idea of a first moment. We end with the paradox transformed, not solved, and that is the honest shape of the frontier where answers come with qualifiers. Perhaps the universe did not expand into nothing, because nothing was never on the menu, and the container picture was always the wrong metaphor. Perhaps what we call emptiness is a physical state with fields, energy and fluctuations, and those ingredients are sufficient to drive dramatic expansion. Perhaps what we call the beginning is a boundary of description, not a moment in a pre-existing time, and the boundary shifts as our theories deepen. The edge is gone, the center is gone, and now even the start begins to blur, not because we are careless, but because nature may be subtler than our grammar. The last images linger on the CMB again, that ancient light wrapped around us like a dim sphere, then fade into a modern sky of galaxies. The narrator can ask quietly what it means to demand a first moment when our best models replace first with earliest describable. Is the beginning a point, a phase transition, or a limit of language, and would we recognize the difference if the data allowed multiple stories? The questions are not rhetorical flourishes, they are boundary conditions for thought, because cosmology is forced to reason where experiments cannot be repeated. In that sense, the mystery is not a gap in knowledge alone, but a test of what it means to know. The next question returns us to the present, where expansion is accelerating again, and the symmetry with inflation becomes impossible to ignore. If early acceleration came from an inflationary vacuum-like component, what drives acceleration today, and why does it resemble a vacuum term so closely? What is expansion made of now, and why did it switch from slowing down to speeding up after billions of years dominated by matter and radiation? If the universe does not need an outside, then the real mystery is internal and persistent, written into the stress-energy content of space-time itself. It is why space-time has the properties it has, and why its geometry keeps changing at all, as if the universe is still rewriting its own metric. We left the early universe accelerating, then slowing as matter took over and clumped into structure. Now the shock is that the slowdown ended, and acceleration returned quietly, long after the first fireworks faded. The central question stays fixed, but the emotional weight shifts with cosmic age and scale. If space expands without an outside, what does acceleration mean when the universe is old, cold, and already filled with galaxies? We're no longer asking about beginnings alone, we're asking what the late universe is becoming. Visually, the change is subtle at first, almost like a time-lapse you can't see in real time. We're not watching a rocket ignite or a shockwave sweep across the sky. We are watching the spacing between distant galaxies change in time, an alteration in the geometry that only becomes obvious when we compare epochs. On screen, the camera can drift through a deep field image, where galaxies hang like faint embers in black water. Nothing seems to move, yet the story is hidden in the light's travel time. The universe reveals its dynamics only when we treat distance as a historical record. In the late 1990s, two teams chased a practical goal, measuring cosmic deceleration with real data, The Supernova Cosmology Project and the High-Z Supernova Search Team targeted Type Ia supernovae because they are bright enough to be seen across billions of years. Their work leaned on decades of earlier supernova classification, but it demanded a new level of precision. The method sounds almost simple, but the execution is brutally delicate and relentlessly statistical. You must find a transient point of light in a crowded field, confirm its type spectroscopically, and measure its brightness precisely while it rises and fades. You must also measure its redshift, because redshift is the clock that tells you how far back in time you're looking. The search itself is a choreography of subtraction and patience. Telescopes revisit the same patch of sky, then software subtracts yesterday's image from today's. What remains is a tiny difference. 1 pixel's rebellion against the stillness, flagged for human scrutiny. Type Ia supernovae are not random explosions. They follow a recognizable script with a narrow cast of physical possibilities. A carbon, oxygen white dwarf in a binary system approaches a critical mass, ignites runaway thermonuclear burning, and unbinds itself in seconds. The blast synthesizes nickel-56, whose radioactive decay powers the light curve we observe. The energy release is staggering, yet it is also strangely orderly. The burning front races through degenerate matter, where pressure does not rise fast enough to halt the reaction. In plain terms, the star cannot expand to cool itself, so the fusion runs away. A Type Ia explosion is not perfectly identical, but it is calibratable. This is the crucial nuance. Light curve shape and color corrections turn messy fireworks into a distance tool with controlled scatter, because brighter events decline more slowly in a measurable way. The supernova becomes a standardizable candle, not a perfect standard candle. That empirical link, first sharpened in the 1990s, is often called the Phillips relation. It is not magic, and it is not purely theoretical either. It is a disciplined statistical bridge between the physics of the explosion and the observed brightness evolution. Behind the scenes, the calibration is a fight against small biases that can masquerade as cosmic acceleration. Selection effects favor brighter supernovae at high redshift, and host galaxies differ in dust and stellar populations. Each correction is modest, yet the conclusion depends on their collective honesty. To use that bridge, observers must correct for dust reddening, instrumental response, and the fact that the universe stretches time itself. A supernova at high redshift appears to evolve more slowly, because cosmological time dilation expands the light curve by a factor of 1 plus z. That stretching is not a nuisance. It is a signature that the redshift is truly cosmological. The spectra also carry a quiet confirmation. Absorption features slide to longer wavelengths in a pattern that matches expansion, not local motion through space. In the data, the universe is not a metaphor. It is a measurable transformation of light. Astronomers built a Hubble diagram, plotting supernova brightness against redshift across many lines of sight. The curve did not match a universe slowing under gravity, even with dark matter included in the energy budget. The data points sat systematically off the expected track, not randomly scattered around it. Distant supernovae looked dimmer than expected for their redshifts. The simplest reading was that the universe expanded less in the past, then began expanding faster later, so the light had farther to travel than a decelerating model would allow. In effect, the distance, redshift relation, carried the fingerprint of a changing expansion rate. On screen, this becomes a bend in a graph that feels like a revelation. The decelerating curve is smooth and confident, then the data drift away from it. Quietly at first, then unmistakably. A best fit line that includes acceleration slides into place, and the residuals suddenly look honest. This was not a single data point, and it was not a single team's idiosyncrasy. It was a pattern across redshifts, repeated across different telescopes, different reduction pipelines, and different patches of sky. Time dilation in supernova light curves supported the cosmological interpretation, not dust or local tricks. Dust, after all, leaves fingerprints that are hard to erase. Ordinary dust reddens light in a wavelength-dependent way, and grey dust would have to be tuned to hide without leaving other observational consequences. The supernova spectra, colours, and the consistency across environments made the dust escape route feel increasingly implausible. The result landed like a second inflation, but stretched across cosmic time rather than compressed into an instant. The universe was not merely expanding, it was accelerating again, as if emptiness had acquired pressure and decided to participate in gravity. The phrase sounds poetic, yet the inference came from careful comparisons of brightness, colour, and redshift. That phrase sounds poetic, yet the mathematics is blunt and almost indifferent to our intuition. General relativity already contained the mechanism in plain sight, waiting in the equations that describe a homogeneous expanding universe. In the Friedmann acceleration equation, energy density is not the only source of gravity. Pressure also gravitates. This is one of relativity's most counterintuitive lessons, and it arrives without apology. In Newtonian intuition, pressure is a local push, and gravity is a pull from mass. In Einstein's theory, pressure is part of the stress, energy tensor, and it contributes to curvature just as energy density does. If pressure is sufficiently negative, the right-hand side flips sign. Expansion accelerates, not because galaxies push outward through space, but because the metric's evolution changes in time. The geometry itself responds to the total energy and pressure content. The simplest term with that behavior is the cosmological constant, L, which Einstein introduced and later regretted. Historically, it was first a mathematical patch to allow a static universe, before Hubble's observations made expansion unavoidable. In modern cosmology, L acts like a constant energy density of space, with pressure equal to minus that density. It is uniform, persistent, and indifferent to dilution. In that model, the equation of state parameter W equals -1. Matter has you near zero because its pressure is negligible compared to its energy density. Radiation has you near 1/3 because photons carry pressure as well as energy. These values are not arbitrary. They encode how each component responds when the universe stretches. The scaling is the key intuition, and it is the reason the late-time surprise is even possible. Matter dilutes as 1 over a cubed as the scale factor A grows, because the same particles occupy more volume. Radiation dilutes as 1 over a to the 4th, because each photon is also redshifted to lower energy. L does not dilute at all, and that single fact reshapes the entire timeline. Its density stays constant even as space expands, so its total contribution grows with the volume of the universe. That sounds like energy appearing from nowhere, yet in general relativity, global energy conservation is not defined the way it is in a static spacetime. So a tiny L can be irrelevant early, then dominate late, without ever changing its own value. The universe coasts through a long matter era, building galaxies and clusters, then crosses a threshold where vacuum-like energy wins. The transition is not a sharp event, but a gradual takeover that becomes obvious only in hindsight. The timing creates the so-called coincidence problem, which is really a question about perspective and cosmic bookkeeping. Why does dark energy become important roughly when galaxies and observers exist, rather than far earlier or far later? Why do we live near the handoff between matter dominance and dark energy dominance? Some answer by invoking selection effects, others by searching for deeper dynamics. But the discomfort remains, because L is constant and the matter density is not. If the two become comparable only briefly in cosmic history, why are we here during that brief overlap? The question is not just philosophical, it is a clue that our model may be incomplete. L is not the only possibility, and cosmology treats it as a hypothesis to test rather than a final truth. A dynamical field, often called quintessence, can mimic L while slowly changing in time. Instead of a fixed vacuum energy, the universe would contain a new component with evolving pressure. For quintessence, W can differ from -1 and can evolve with redshift. The field rolls down a potential energy landscape, and its kinetic and potential terms set the effective W. In plain language, it behaves like a fluid whose stiffness changes as the universe expands. Measurements try to constrain W and its redshift dependence, because different histories change distances and growth. A small deviation from W equals -1 would ripple through the Hubble diagram, the angular diameter distances, and the rate at which cosmic structure forms. Even a subtle tilt in W changes how quickly overdensities stop growing. Observationally, supernovae are only one leg of the case, and they are strongest when paired with independent rulers. Baryon acoustic oscillations provide a standard ruler, and the CMB anchors the early universe calibration. Together, these probes form a cross-checking system, each with different systematics and different sensitivities. Baryon acoustic oscillations are the fossil imprint of sound waves in the early plasma. Before recombination, photons and baryons were tightly coupled, and pressure waves propagated outward from overdensities. When the universe cooled enough for atoms to form, those waves froze into a preferred scale. That scale, about 150 megaparsecs in today's units, appears as a subtle bump in the clustering of galaxies. It is not a ruler you can hold, but it is a statistical ruler written into the cosmic web. By measuring its apparent size at different redshifts, we infer how the expansion stretched space. The CMB, meanwhile, is the oldest light we can see, a snapshot of the universe at about 380,000 years. Its temperature anisotropies encode the geometry and composition of the cosmos, and they set the sound horizon scale that BAO and other probes rely on. The acoustic peaks are like harmonics in a drumhead, except the drumhead is space-time. Together they constrain the expansion history and the geometry, and they also constrain spatial curvature. In the simplest fit, W is consistent with -1 within errors, and the data prefer a L-like component. The universe looks remarkably close to flat, and remarkably close to LCDM. Yet the fit is not the end of the story, because the physics behind L is unclear. The cosmological constant is mathematically simple, but conceptually explosive, because it seems to connect cosmic acceleration to quantum vacuum energy. The same term that stabilizes the equations destabilizes our understanding. In quantum field theory, the vacuum is not empty. Fields have zero-point fluctuations, and their ground state energy contributes an effective vacuum energy density. Even in perfect darkness, the quantum fields still have irreducible jitter. You can picture it as a restless baseline, a minimum hum that never turns off. Virtual particle, antiparticle pairs flicker in and out of the formalism, and modes of every field contribute half a quantum of energy per oscillation. The vacuum is not nothing, it is a structured state. If you estimate that energy with a naive cutoff, the number is absurdly large. It overshoots the observed dark energy density by tens of orders of magnitude, depending on where you place the cutoff. If you cut off at the Planck scale, the mismatch becomes almost unimaginably severe. This mismatch is the vacuum catastrophe, one of the worst predictions in physics. It is not a small discrepancy to refine with better data. It is a clash of frameworks, because quantum field theory and general relativity each seem internally successful, yet together they scream. The observed dark energy density is tiny in particle units, yet it dominates the cosmic budget today. The universe accelerates under a term that looks like almost nothing. In everyday terms, the energy density is comparable to a few protons per cubic meter, spread smoothly through space. So the paradox sharpens, and it sharpens in a way that feels almost personal. The universe seems driven by the energy of empty space, but our best theory of emptiness predicts the wrong value by a staggering margin. It is as if the universe is whispering a number, while our equations shout a different one. Some hope the vacuum energy cancels through symmetry or renormalization, leaving only a small residual. In quantum field theory, we often subtract infinities in a controlled way, and only energy differences matter for many experiments. But gravity couples to absolute energy in a way that makes simple subtraction feel like cheating. This is where the mystery becomes physical rather than philosophical. If vacuum energy gravitates, then it should curve spacetime, and the curvature should be enormous. The fact that it is not enormous suggests either a hidden cancellation mechanism or a misunderstanding of what counts as gravitationally active energy. Others hope dark energy is not vacuum energy at all. A rolling field could have a small energy scale set by dynamics, though it must be extraordinarily light and stable. Its mass would have to be comparable to the present Hubble scale, unbelievably tiny by particle standards. But such a field must also avoid obvious side effects, and that is where models become constrained. It cannot couple strongly to ordinary matter, or it would create new forces we would have detected in laboratories and in the solar system. In practice, quintessence models often require careful screening or extremely weak couplings. Modified gravity is another route, changing the left side of Einstein's equations instead of adding a new component. The goal is to reproduce acceleration without a new energy density, by altering how gravity behaves on the larger scales. But any modification must match solar system tests and CMB constraints. That requirement is punishing, because nature has already graded general relativity in multiple arenas. General relativity has passed precision tests near Earth, around the Sun, and in binary pulsars, where strong field effects matter. A viable modification must hide locally. then reveal itself only across cosmic distances, an elegant trick if it exists. At this point, the documentary's theme returns with force, and the word nothing becomes less innocent. Nothing is not a neutral background, because in modern physics the vacuum is a structured state. Even the emptiest region of intergalactic space is filled with fields, fluctuations, and a geometry that can evolve. Even if dark energy is L, it is not an outside fluid pressing in from beyond the universe. It is a property of space-time itself, influencing how the scale factor evolves everywhere at once. It is not located in one place, and it does not flow like a wind. That distinction matters when people ask why galaxies are not being torn apart. If space expands, why does the Milky Way not swell, and why do atoms not stretch? The question is natural, because expansion sounds like a force acting on everything. The answer is that expansion is not a universal force acting on all scales. Metric expansion is a large-scale solution for an almost uniform universe, while local systems are dominated by binding forces and local curvature. The equations that describe the cosmic average are not the same as the equations inside a galaxy. Gravitationally bound structures decouple from the Hubble flow, and that decoupling is more than a slogan. Once matter collapses into a halo, the local geometry is no longer well described by pure Fell-Lable. The region becomes a patchwork of potentials, orbits, and virialized motion. Inside galaxies and solar systems, gravity and orbital dynamics set stable sizes. A planet remains in orbit because its local gravitational binding energy overwhelms the feeble effect of cosmic expansion. The same is true for stars in a galaxy, and for galaxies in a bound group. Electromagnetic forces bind atoms and solids far more strongly than cosmic expansion could pull. The characteristic scales of atomic structure are set by quantum mechanics and charge, not by the Hubble parameter. If you tried to attribute atomic size changes to cosmic expansion, the numbers collapse immediately. A useful rule is that expansion is negligible where the dynamical timescale is short. Local physics re-equilibrates faster than the metric changes, so bound sizes stay fixed. In other words, if the system can respond quickly, it simply does not notice the slow stretching of the cosmic background. This is why Andromeda can approach us while the universe expands. Peculiar velocities and local potentials ride on top of the global expansion, not inside an expanding container. The local group is a gravitationally bound island, and within it, gravity writes the dominant story. So acceleration does not mean everything is stretching like rubber. It means that on large scales, the distance between co-moving world lines grows with increasing rate. The expansion is encoded in how we map coordinates to physical separations, not in a universal tearing. Now the chapter turns from discovery to consequence, and the tone shifts toward the long future. If acceleration continues, the future is not a dramatic crash, but a slow erasure of accessible structure. The universe does not end with an explosion, but with a fading. In an L-dominated universe, the scale factor grows roughly exponentially at late times. The Hubble parameter approaches a constant, and an event horizon forms. The expansion becomes close to de Sitter, like a space-time with a steady, relentless outward drift in commoving separation. An event horizon is not a wall in space, it is a limit on causal contact. Beyond a certain commoving distance, light emitted now will never reach us. The horizon is drawn by the geometry of space-time and the finite speed of light. It is worth pausing on how strange that is, because it reverses a familiar intuition. In a decelerating universe, distant regions can eventually come into view, because the expansion slows and light can catch up. In an accelerating universe, the expansion wins, and some regions are lost forever. As time passes, more galaxies cross that horizon and fade, not by moving through an edge but by slipping out of reach. Their light becomes redshifted, stretched to longer wavelengths, then diluted into undetectability. The photons do not stop existing, but they become so cold and so sparse that they blend into the background. Visually, we can imagine a galaxy's last photons arriving like a slow drizzle. The spectrum slides from visible to infrared, then to radio, then to wavelengths larger than solar systems. The image blurs, dims, and finally becomes a mathematical memory. This creates a kind of observable nothingness, and it is a nothingness with strict definitions. Not an external void the universe expands into, but a growing region of space-time that can no longer exchange signals with us. The emptiness is not a place, it is a causal condition. The sky's future becomes lonelier even if space remains full of distant matter. The loss is informational, because causal disconnection removes those regions from our physical reach. What exists beyond the horizon still exists, but it cannot affect us, and we cannot affect it. Locally, the Milky Way and its bound group remain, and their internal drama continues. Stars orbit, gas clouds collapse, and occasional supernovae flare. But beyond the gravitationally bound island, the cosmic web slips away, leaving a darkening, thinning horizon. This is the heat-death scenario in its modern form, and it is less cinematic than it is absolute. Stars burn out, gas is used up, black holes evaporate over unimaginable times, and usable free energy declines. The universe approaches a state of maximum entropy, where gradients vanish. L does not rip structures apart, it simply prevents new large-scale structure from forming. Expansion outpaces gravitational collapse on the bigger scales, freezing growth. Clusters stop accreting, filaments stop thickening, and the cosmic web becomes a fossil of its earlier self. That difference between expansion and structure growth is central to understanding what we're seeing. The universe can expand faster while the formation of new clusters slows, because density contrasts stop amplifying efficiently. Gravity still works, but it loses the race against the background stretching. In the matter era, gravity won the long game and built the cosmic web. Overdensities grew, merged and deepened, turning tiny primordial fluctuations into galaxies and clusters. In the dark energy era, the background expansion wins and the web's growth stalls. Quintessence changes the details, and W becomes the dial that sets the tempo. If W is greater than -1, acceleration can weaken, and horizons and fate can shift. The universe might still accelerate, but less relentlessly, and the horizon scale could evolve differently. If W is less than -1, the story becomes stranger, because phantom energy grows with expansion. Instead of diluting or staying constant, its density increases as the universe expands, making the acceleration intensify rather than settle. The geometry becomes unstable in a very specific way. In that case, the universe can end in a big rip. Bound structures are eventually torn apart, first clusters, then galaxies, then solar systems, then atoms. The sequence is not arbitrary, because each structure has a characteristic binding scale that must be overcome. The Big Rip is not favoured by current data, but it remains a logical possibility. Measurements of W test whether dark energy is truly constant or slightly unstable. Each incremental improvement in calibration and sample size tightens the leash on exotic futures. Another fate is recollapse, a big crunch if dark energy changes sign or decays. A future phase transition could end acceleration and let gravity retake control. In that scenario, the expansion could slow, stop and reverse, turning the cosmic clock toward contraction. But observations currently point the other way. The combined data favour a flat universe with about 70% dark energy, consistent with a constant L. The simplest model keeps surviving, and its survival is itself a clue. This is where the chapter's mood becomes eerie, because the simplest model is also the most conceptually disturbing. The universe may be headed toward emptiness as a dominant theme, but it is not headed toward literal nothing. The nothing is never truly empty, and it never truly stops acting. Even an almost empty universe still has geometry, horizons, and vacuum structure. It still has quantum fields in their ground states, and it still has a metric evolving. The stage remains even as the actors leave. The paradox returns in a new register. The universe does not expand into an external void, yet acceleration makes the observable universe look increasingly like a void. The emptiness is not outside the cosmos, it is inside our future light cone. We can describe the future as an island universe, surrounded not by space outside the cosmos, but by regions of space-time that have slipped beyond causal reach. It is a solitude created by the rules of relativity, not by a boundary in space. That is a subtle form of edge, created by dynamics, not topology. It is an edge of information, defined by light cones in an accelerating geometry. The universe can be spatially unbounded and still present each observer with a finite, shrinking domain of influence. The event horizon also rewrites what future observers could infer about cosmic history. Far in the future, the CMB will be redshifted to wavelengths larger than any practical detector, its temperature will drop below the noise floors set by local astrophysical processes. Distant galaxies will disappear beyond the horizon, leaving only the local group's remnants. The evidence for expansion could become inaccessible, making cosmology harder from within. The universe would still be expanding, but the observational scaffolding would be gone. The universe would still be expanding, but the clues would be gone. The paradox would remain, but the data that forced the right interpretation would fade. Future astronomers could look up and see a quiet, static-looking sky, and draw the wrong conclusion. So dark energy is not only a component in an equation, it is a force shaping what can be known, because it reshapes causal structure and hides the wider universe. It edits the accessible archive of the cosmos, one horizon crossing at a time. This brings us back to the vacuum catastrophe with added urgency. If L is real, it is the energy of empty space, and we do not understand why it is small. The number is not merely puzzling, it is telling us that our understanding of vacuum and gravity is incomplete. If L is not vacuum energy, then we must explain why it behaves like vacuum energy so precisely. Either way, nothing is doing something measurable. The vacuum is not a passive absence, it is an active ingredient in the universe's expansion history. The chapter now ties back to the Hubble tension introduced earlier, because the expansion history is the bridge between early and late measurements. Late-time acceleration affects distance inferences, and model assumptions propagate into H0 estimates. When the model shifts, inferred distances shift with it. Local distance ladders measure H0 directly from nearby calibrators and supernovae. They build outward step by step, from parallax to Cepheids to TPE supernovae, and they rely on careful control of astrophysical systematics. Their strength is directness, and their weakness is calibration complexity. CMB inferred H0 depends on the early universe model and the sound horizon scale. It is not measured as a speed in the CMB map, but inferred by fitting a cosmological model to the acoustic peaks. Its strength is precision, and its weakness is model dependence. If dark energy is L, the standard model is tightly constrained, and the tension looks like either systematics or new early universe physics. If dark energy evolves, late-time fits shift, and the inferred H0 can move. That possibility keeps the question open without rewriting the entire story. The tension therefore becomes a stress test of the whole narrative. It asks whether our expansion history is missing a component, either early or late, that changes inferred distances. It also asks whether we have underestimated the difficulty of measuring the universe with imperfect instruments and imperfect astrophysical candles. But even if the tension resolves, dark energy remains the climax problem. It is the second acceleration, echoing inflation, hinting at a deep link we do not yet see. It is as if the universe has used the same grammatical structure twice, once at the beginning and once near the end. Inflation used a vacuum-like term to stretch the early universe smooth. Dark energy uses a vacuum-like term to stretch the late universe empty, and both raise the same question. Why does the vacuum behave like a source of repulsive gravity, and why does it take the values it does? What is the vacuum, and why does it gravitate with the value it has? Why does spacetime carry an energy scale that is tiny, stable, and yet cosmologically decisive? Why is the vacuum not simply zero? And why does the universe care about its baseline? Here the documentary leans into the mystery without surrendering precision. The universe is not expanding into nothing, but the fate of expansion is a cosmos dominated by near nothing. The emptiness becomes the main character, not because it is truly empty, but because it controls the geometry. A L-like future is not a collapse into an external void. It is an internal geometric evolution where more of spacetime becomes causally irrelevant to any given observer. The universe does not need an outside to become isolated from itself. The word outside becomes less useful than the word horizon. The universe does not need an exterior to lose contact with itself because relativity already limits influence. Acceleration tightens those limits, turning distance into disconnection. Transition. We have traced acceleration from data to destiny, and the paradox now sits in the open. The final step is to return to the question that started the entire film, and to handle it with care. When we ask what the universe expands into, we are mixing geometry with container language. We are borrowing intuition from rooms and boxes, then applying it to space-time. Dark energy makes that mistake feel tempting again, because it makes emptiness powerful. If empty space can accelerate expansion, It feels like a substance filling a container, pressing outward. Yet the lesson is the same as before, only sharper and colder. Expansion is not motion through a surrounding nothing. Expansion is the changing metric of space-time, and acceleration is the metric changing in a particular way. The universe is not a thing moving into a place. It is the set of distances changing among world lines. In the next chapter, we stop circling the grammar trap. We answer cleanly what into what means, and why the universe never needed an outside. The mystery will remain, but the question will finally be phrased in the language the universe actually speaks. Transition. After beginnings and endings, we return to the paradox itself and we resolve it without metaphor. We return to the opening hook and the stubborn intuition it triggers, because it feels almost physical in the gut. Imagine standing at the edge of everything, looking for a rim or a wall, then learning there is no edge at all. If the universe expands, what could it be expanding into? The direct answer is technical, and it is also the cleanest description we have. Cosmological expansion is metric expansion, meaning the rule for distance inside space-time changes with time. Galaxies are not flying into emptiness because the geometry between co-moving world lines is what evolves. In general relativity, space is not a container that sits still, while contents move around inside it. The metric defines intervals, proper times, and proper distances, and it behaves like a dynamical field. When the metric evolves, the measured separation between co-moving observers increases, even if their coordinates stay fixed. Visually, you can picture a faint grid drawn across the cosmos, then imagine the grid itself stretching. The points on the grid can remain labelled the same, yet the ruler you lay between them reads a larger number. That is the heart of the idea, and it is why the into what question misfires. The scale factor is our compressed name for that change, and it carries an entire history in a single symbol. In an FLRW universe, proper distances scale roughly with a t for co-moving points. Saying the universe expands means a t increases, not that matter crosses a boundary. This is why the phrase expanding into nothing misleads, even though it sounds reasonable in ordinary speech. It imports container thinking from everyday life, where objects grow inside rooms and spill into surrounding space. In cosmology, there is no pre-existing room, because the room is the geometry being described. A better phrasing is simple and less intuitive, and that is why it initially feels unsatisfying. Space is expanding, or the scale factor increases, or the metric evolves over cosmic time. These phrases sound abstract because they refuse to invent an outside that the equations never require. We also reframe what nothing can mean, because the paradox hides a definition swap that happens without warning. Nothing might mean empty space with no atoms, which still has geometry and fields, and still permits light to travel. Nothing might mean a quantum vacuum, which still has fluctuations and stress energy, even when no particles are present. Nothing might also mean no space-time at all, which is beyond standard general relativity and beyond our everyday imagination. In that deeper sense, nothing is not an emptiness you can stand inside, because there is no inside. The word remains useful, but it becomes slippery at the edges of theory. In the cosmological model we actually use, there is no physical outside built into the description. Space can be infinite with no edges, so there is nowhere to expand into. Space can also be finite without boundaries, like a three-dimensional analogue of a sphere's surface. Finite without boundary is the key to dissolving the edge picture, because it breaks the link between finite and walled off. A closed universe has a finite volume at any time, yet no boundary where physics ends. Asking what lies beyond that boundary is like asking what lies north of the North Pole. If you linger on that image, it becomes clearer why the intuition struggles. On Earth, you can walk and never find an edge, yet the surface area is still limited. The geometry closes on itself and the outside is not part of the surface's own rules. Even if the universe is spatially infinite, the outside question still fails for a different reason. Infinity does not come with an edge that can move outward like a frontier. Expansion then means that distances between co-moving points grow everywhere, not that the whole infinite set shifts into a larger arena. This is where earlier metaphors must be handled carefully, because they help and harm at the same time. The balloon analogy helped because it showed intrinsic expansion without a center on the surface. It misleads when viewers imagine the balloon expanding into the surrounding room. because the room is not part of the surface physics. General relativity does not forbid embedding, but it does not require it either, and that distinction matters. You can mathematically embed a curved space in a higher dimensional space for visualization, the way a curved sheet can be drawn in a larger room. That embedding space has no physical status unless a deeper theory adds it as a measurable ingredient. Historically, this shift was one of the great conceptual shocks of the 20th century. Einstein's 1915 theory replaced gravitational force with curvature, and within a few years, Friedman and Lemaitre found expanding solutions that were not mere mathematical curiosities. The idea that the universe could be dynamic was not an add-on. It was already hiding inside the equations. The universe, as modelled, is self-contained in its geometry and contents, and that is the point worth repeating in plain language. Einstein's equations relate curvature to stress energy within space-time, linking how matter moves to how distances are defined. The equations do not ask for an external coordinate volume that must be filled. We can now connect the language trap to the evidence that forced this framework, because the observational trail is unusually concrete. Redshifts are measured as shifts in spectral lines, giving a dimensionless z that anyone can compute from wavelengths. In an expanding metric, z encodes the ratio of scale factors between emission and observation. That link is not metaphor, it is operational, and it is testable with instruments. Photons travel along null geodesics, and their wavelengths stretch with the evolving geometry. The observed redshift tracks the history of AT along the light path. If you could watch it as an animation, the light would leave a galaxy as tightly spaced wave crests. As the photon crosses the expanding grid, the crests spread apart, not because the photon tires, but because the metric changes the meaning of distance. By the time it reaches us, the same light carries a longer wavelength. Supernova time dilation reinforces the same story with a separate clock built into the sky. Light curves are stretched by a factor of 1 plus z, matching expansion rather than tired light alternatives. The universe is not merely dimmer at distance, it is slower in observed time. The cosmic microwave background adds a second, older anchor, and it carries the texture of the early universe in a single glow. Its blackbody spectrum and temperature scaling fit a cooling universe with T proportional to 1/A. The anisotropy pattern encodes geometry, composition, and the acoustic history of the early plasma. Here the visuals almost narrate themselves, a faint ancient light mapped across the whole sky, with tiny temperature differences like ripples on a pond. Those ripples are not noise, because they line up with predictions of sound waves in a hot, ionized early universe. The peaks and valleys in the power spectrum act like a ruler for cosmic curvature. Primordial element abundances add a third pillar, and they do it with chemistry rather than photons. Deuterium, helium, and lithium ratios reflect nuclear reaction rates in an expanding, cooling universe. These independent lines converge on the same expansion narrative. So what can we say with confidence, without overselling what remains uncertain? Expansion is supported by multiple, cross-checking observations that do not rely on one fragile assumption. General relativity provides a coherent, self-contained description of expansion as evolving geometry. We can also say what expansion does and does not mean locally, because this is where intuition often overreaches. Bound systems do not expand with the Hubble flow in any simple way, and the reason is straightforward. Local gravity, electromagnetic forces and pressure gradients dominate, and the FLAW-W description is an average over large scales. On the screen, this can be shown with nested scales, a galaxy cluster drifting with cosmic expansion, while inside it stars orbit steadily, and inside those stars atoms keep their familiar sizes. The stretching is not a universal rubber sheet that pulls everything apart equally. It is a statement about the large-scale metric that best fits the universe when you smooth over enough distance. We can now place horizons where the outside fantasy used to sit, because horizons feel like edges even when they are not. A horizon is not a boundary of space, it is a boundary of observability. The particle horizon limits what we can see from the finite age of the universe. The event horizon, in an accelerating universe, limits what can ever influence us, even in principle. Distant galaxies can exist and still become causally irrelevant over time, as expansion outruns signals. The universe can be unbounded and still present each observer with a finite, changing cosmic domain. This is why the edge intuition feels so persistent, and why it keeps returning even after the math is explained. Our brains treat the observable universe as the whole universe, because that is how perception works in daily life. Cosmology forces a separation between what exists and what is observable. We also revisit the energy question that bothered careful viewers, because it exposes another everyday assumption. Photons arrive with less energy after redshift, and it feels like energy vanished into the void. In an expanding space-time, global energy conservation is not defined the Newtonian way. Locally, energy momentum is conserved through the covariant divergence condition, and that local statement is extremely strict. Globally, a time-dependent metric lacks a universal time translation symmetry, so there is no single conserved total energy. The redshift energy does not have to go anywhere. This is unsettling, but it is consistent with how the theory is built, and it follows a deep pattern in physics. Conservation laws follow from symmetries, and the expanding universe does not have the symmetry that would guarantee global energy conservation. The bookkeeping changes because the geometry changes. Now we acknowledge the open problems that remain after the paradox is resolved, because a solved confusion is not the same as a finished science. Dark energy is inferred from the expansion history, but its nature is unknown. It could be a cosmological constant, a dynamical field, or a sign of modified gravity. Inflation is strongly motivated and partially supported, but not fully pinned down, and that nuance matters. The simplest predictions match many CMB statistics, yet the mechanism and energy scale remain uncertain. Primordial gravitational waves remain a key test, still not decisively detected. The beginning question remains open in a deeper sense, even if the outside question does not. Classical GR points to geodesic incompleteness when extrapolated backward, which signals missing physics rather than a literal moment of creation. Quantum gravity may replace the singular boundary with a bounce, a nucleation event, or something else. Even the word nothing becomes unstable at that frontier, because the theory may not permit the concept we are trying to use. If space-time is quantized, then geometry itself may be emergent from more primitive degrees of freedom. In that regime, asking what is outside or before may be a category error. We also carry forward the Hubble tension as a live stress test, because it reminds us that precision can expose cracks. Local distance ladders and CMB inferred values disagree beyond quoted uncertainties. The resolution could be systematics, or it could be new physics that slightly reshapes early expansion. None of these uncertainties restore the need for an outside, and that is the important constraint to keep in view. They change the contents and dynamics inside the model, not the requirement for a container beyond it. The paradox was never a missing place, it was a misleading grammar. Transition. After beginnings and endings, we return to the paradox itself, and we resolve it without metaphor. So we answer the central question in one sentence that can hold the whole film, even when the visuals go quiet. The universe expands by changing the metric that defines distance, not by moving into external emptiness. The room is not a background, because the room is what is evolving. This resolution is satisfying, and it is also a little cold, like a clear night sky that refuses to blink back. It tells us the outside is not hidden, it is undefined in the model. The demand for an exterior is a habit formed in a world of boxes and borders, yet the paradox does not vanish, it transforms into a deeper question that the camera can linger on. Why does space-time have these equations, these symmetries, and these particular constants? Why is there a universe with laws describable by mathematics at all? We end where geometry becomes narrative, and the visuals can become almost minimal. The universe is a story written into the structure of space-time, with matter and light as its punctuation. Nothing is not a place beyond an edge, it is a limit of language at the boundary of understanding. Transition. The paradox is solved, but the mystery remains, and it now points inward. Across this journey, the paradox slowly changed shape, from a childlike picture of galaxies rushing into emptiness to a precise claim about geometry itself evolving. We followed the clues written in light, redshifts in atomic lines, supernova time dilation, the CMB's near-perfect blackbody glow, and primordial elements, until expansion became a measurable stretching of the metric, and we learned that the universe's story is paced by what fills it, radiation and matter slowing the growth, dark energy speeding it up again, while horizons and curvature set hard limits on what any observer can ever confirm. Along the way, nothing stopped being a simple word, and split into competing ideas with very different physical meanings. Empty space is still a stage with rulers and clocks, a geometry that can curve and evolve, and fields that can store energy and pressure. The quantum vacuum is not blank either. It fluctuates, it polarizes, it gravitates, or at least it should, which is why the tiny measured value of dark energy feels so outrageous. And no space-time at all is a deeper kind of nothing, one that general relativity cannot describe, and that we only meet when we run the film backward to the edge of its own validity. That edge is the place we call the Big Bang, not as a point in space, but as a limit in our equations where time, distance, and curvature stop behaving classically. Inflation offered one possible bridge across some early puzzles, smoothing the universe and planting the seeds of structure. Yet it also pushed the ultimate origin question further into the shadows. Dark energy then returned as a second surprise, turning deceleration into acceleration, adding an event horizon to the far future, and forcing us to admit that the dominant ingredient of the cosmos is still unidentified. Even our best measurements strain under the Hubble tension, a disagreement that may be mere calibration, or maybe the universe hinting that our expansion history is incomplete. What held all of these chapters together was a single shift in perspective, from thinking in containers to thinking in relationships. In general relativity, distances are not laid onto space, they are defined by the metric, and the metric is part of the physics. The scale factor AT is not a speed through an external medium, it is the bookkeeping of how spacetime's own distance rule changes with cosmic time for comoving observers. When photons redshift, their wavelengths stretch with that evolving geometry, and the missing energy is not dumped anywhere, because a changing spacetime does not guarantee a global conservation law to balance the books. So the universe is not expanding the way smoke expands into air, or shrapnel expands into a room. It expands the way a geometry can expand intrinsically, without needing a surrounding space to expand into. That is why there is no center to locate, no edge to approach, and no cosmic wall to press against, even if the universe were finite in volume. What we can map are horizons, the boundaries of observation and influence, drawn not by walls, but by the finite speed of light and the changing rate of expansion. In the end, the question, what is it expanding into, turned out to be less a scientific mystery than a linguistic trap. It smuggles in the assumption that space is a thing sitting inside another thing, when our best description says space is the web of distances, and the web itself can stretch. The more faithful question is not where the universe is going, but what the universe is becoming, as its geometry evolves under the weight and pressure of everything it contains. Still, the resolution of the paradox does not shrink the wonder, it relocates it. If expansion needs no outside, then the most haunting nothing is not beyond an edge, but beneath the laws themselves. Why does spacetime exist in a form that can be described by a metric at all? Why do quantum fields inhabit it? And why does vacuum energy gravitate with a value so small that it looks almost like a cosmic rounding error? And if time is part of the geometry, then asking what came before may be like asking what lies north of the North Pole. An invitation to reframe, not a door we simply failed to open. The universe we can measure is already strange enough to be real, a cosmos where recession can exceed the speed of light without breaking relativity, where the oldest light is a cooled whisper of a hotter past, and where the future may be an ever emptier sky. Yet it is also a cosmos that keeps offering stress tests, from the Hubble tension to the nature of dark energy, daring us to tighten our measurements and sharpen our theories. Perhaps the next breakthrough will not come from imagining a new outside, but from understanding the inside more deeply, the relationship between geometry, quantum vacuum, and the arrow of cosmic time. And maybe that is the final twist of the space paradox, the one that lingers after the credits. The universe does not expand into nothing, because nothing is not a place waiting beyond the map. The universe expands by rewriting the map itself, then asks us quietly why there is a map at all. So if everything is getting bigger, what could it possibly be expanding into? How do you grow when there's nowhere to go? You grow by changing the meaning of distance, because expansion is not motion through emptiness, it is space-time's geometry evolving from within. When you stop looking for an edge, the true horizon moves inward, to the question of why space, time, and law exist in the first place. The deepest nothing is not outside the universe. It is the idea that there could have been no universe to describe. If this reframed the way you picture reality, Keep asking better questions, follow the evidence, and let the universe teach you what words can't.